Hydrogen, helium, and lithium are not just elements, they are fossils from creation itself. The quest to understand these first light elements reads like a cosmic detective story, where every atom is a clue frozen in the universe's opening minutes. By the end of our journey, you will see how 30 radical theories are testing the very boundaries of known physics to explain what happened in that fiery dawn. The standard model of Big Bang nucleosynthesis stands as one of cosmology's greatest triumphs, predicting the abundance of these simple atoms with stunning precision. Yet deep questions crack its smooth surface. Why does lithium stubbornly disagree with predictions, as though something erased it from the earliest stars? How did ghostly neutrinos shape the fate of all matter? And could exotic physics, perhaps dark matter or hidden forces, have left subtle fingerprints on the primordial cocktail swirling before the first minute was over? This is no dry history lesson. We are going on a guided tour through 30 distinct theories, each proposing a twist in the tale of how the simplest atoms came to be, each pushing against the frontiers of what we know about dark matter, particle physics, and the infant universe itself. So, before we step into the fire of the Big Bang's first 3 minutes, which of these hidden forces do you feel might rewrite the story of our cosmic birth? A searing ocean of energy, barely 3 minutes old, set the stage for everything you see today. The standard model of Big Bang nucleosynthesis is the cosmic recipe that cooked up the universe's first light elements, and its elegance is almost too good to be true. In that blistering infancy, the entire cosmos was a churning particle storm where temperatures soared over 1 billion degrees. Protons and neutrons, the building blocks of atomic cores, ricocheted through a blinding plasma too violent to hold anything together. Then came the cooling. As the universe ballooned outward, heat bled away like a fading ember, finally allowing these particles to stick. The moment the universe slipped below the critical fusion threshold, it began stitching the simplest nuclei, a tender window that slammed shut within a handful of minutes. This rapid assembly line hinged on a delicate dance between protons and neutrons. Free neutrons are unstable outside an atomic core, decaying into protons with a half-life of about 10 minutes. So the clock was ticking furiously. Only a fraction of all the matter was locked into neutrons, roughly 1 for every 7 protons once things cooled enough for them to freeze out. This ratio became the sculpting hand behind every atom that would form. Too few neutrons and the universe would be an empty desert of lonely protons. Too many and heavier elements might have swamped the delicate infancy of stars. It was a tightrope walk across a cosmic abyss. The first real step was building deuterium, a fragile partnership of 1 proton and 1 neutron. This is where things got stubborn. Deuterium is remarkably easy to destroy. Photons, the packets of light racing through the hot plasma, carried enough punch to shatter deuterium the instant it appeared. The universe was a demolition derby, and deuterium was the car that kept getting smashed before it could leave the pit. Cosmologists call this the deuterium bottleneck. Only when the temperature dropped far enough to roughly the heat of the sun's core today did more deuterium survive than was ripped apart. Once that bottleneck broke open, the floodgates burst. Pairs of deuterium slammed together to build helium-3 and helium-4, along with a tiny splash of lithium-7. In a breathtaking chain of smash and grab, nearly all available neutrons were vacuumed up into the staggeringly stable nucleus of helium-4, a particle of 2 protons and 2 neutrons. The entire output of this ancient furnace was guided by one fiercely precise number known as the baryon-to-photon ratio. Baryons are the heavy particles, protons and neutrons, the stuff you and I are made of. Photons are the weightless carriers of light. In our universe today, for every single baryon there are roughly 2 billion photons streaming through space. That sounds like a colossal imbalance, but it means the early universe was overwhelmingly luminous. This ratio acts like a master thermostat and density dial. A higher baryon density would have made the universe a crowded kitchen where more helium smothered the broth. A lower density would have stretched things so thin that deuterium would rarely find a partner at all. By measuring the leftover glow of the Big Bang, the cosmic microwave background, scientists have zeroed in on this number to astonishing accuracy, about 6 parts in 10 billion. It is the tuning fork against which every competing theory resounds, and this is where the Standard Model plants its flag. With a tiny set of inputs, the expansion rate of space, the number of neutrino families, and the lifespan of the neutron, it predicts the primordial abundances of these light elements with jaw-dropping fidelity. Helium-4 should make up roughly 25% of the ordinary matter mass, and measurements of ancient unspoiled gas clouds return almost exactly that number. Deuterium falls perfectly in line with predictions from the cosmic microwave background. It is a staggering success, a razor-sharp alignment between theory and observation that tells us we truly understand the backbone of cosmic history from 3 minutes onward. But that very triumph sharpens the point of every anomaly that refuses to fit. Lithium-7, observed in the atmospheres of the oldest stars, stubbornly contradicts the model, hinting at a piece of the story we have not yet read. The elegant simplicity of this standard kitchen, where a cooling universe, a neutron bottleneck, and a fine-tuned photon ratio built the first flickering light elements, sets the stage for every breathtaking crackpot notion, hidden particle, and unsettling mystery still lurking in the luminous fog of creation. Ghostly particles that pass through you by the trillions each second held the fate of the universe in their grip. Neutrinos are the ultimate cosmic escapists, so aloof that they barely acknowledge other matter exists. But in the furious opening act of the Big Bang, they were the kingmakers of the neutron. Understanding when these shy phantoms slipped away from the rest of creation is key to unlocking why the universe is not a sterile sea of hydrogen. To see why, we have to zoom into the universe at just 1 second old. The entire cosmos was a thrashing, opaque ocean so dense and hot that even neutrinos were trapped, constantly crashing into electrons and positrons in a frenetic swarm. This constant bumping kept the weak nuclear force running like a busy telephone exchange, transforming protons into neutrons and back again without pause. As long as the party stayed this crowded, the ratio of protons to neutrons remained fluid, a seesaw balanced by the blistering heat. But as the universe stretched and cooled, the density plummeted. The neutrinos found themselves with fewer dance partners, their bustling interactions grinding down. Then came the pivotal freeze-out, the moment about 1 second after the Big Bang when the universe became effectively transparent to these ghostly particles. They decoupled, streaming away into the void, their influence over the proton-neutron balance shattered. That snapshot is not just a footnote, it set the neutron count in stone. With a weak interaction silenced, neutrons could no longer regenerate from protons. The ratio that existed right at that decoupling instant became the seed for every nucleus that would ever form. This is where timing becomes everything. If neutrinos had decoupled even a few fractions of a second later, the universe would have been slightly cooler and nature would have favored slightly fewer neutrons. Fewer neutrons means less helium-4 was forged when the deuterium bottleneck finally broke. Decouple earlier in a hotter instant, and you seed the universe with a heavier sprinkle of neutrons, bloating the helium supply beyond what we see today. The helium-4 abundance is a direct fossil of that ghostly parting. Measure it, and you are reading the temperature of the universe at 1 second old with excruciating precision. This makes the neutrino a delicate probe of particle physics beyond our standard model. Scientists suspect there are exactly 3 flavors of neutrinos, the electron, muon, and tau types, all ghostly lightweights. But what if a 4th, heavier sterile neutrino was lurking in that primordial plasma? Even a single extra species would have silently added more energy to the cosmic soup, forcing the universe to expand a whisker faster. A faster expansion would push the decoupling temperature higher, preserving a slightly higher neutron fraction, and thus producing more helium-4 than stars can account for. This is not idle speculation. Observations from the cosmic microwave background and deep surveys of pristine gas clouds have placed a tight ceiling on any such extra relativistic degrees of freedom. The number of neutrino families is essentially locked at 3, plus or minus a tiny sliver of room for error. Yet this avenue of investigation does more than just close doors. It cracks open a window on exotic physics that might subtly adjust the cooling curve. Imagine a hidden sector where dark matter particles were faintly interacting with neutrinos in those first 3 minutes, sapping a little energy away before decoupling. That slight energy drain would shift the freeze-out balance, leaving a tangible mark on the helium and deuterium abundances measured today. The lithium problem, that stubborn shortfall in ancient stars, suddenly becomes a testbed for these hidden forces. If a tiny fraction of the early plasma energy was being diverted by new physics, the neutron-to-proton ratio shifts just enough to trim the predicted lithium-7 without spoiling the perfect match for helium and deuterium. In this view, neutrinos are not mere bystanders but messengers from a deeper reality, their ancient departure shaping the very chemistry of the first stars and every planet that followed. Yet a single stubborn anomaly refuses to align, a ghost in the cosmic machine that haunts the standard model. Lithium-7, the third lightest element forged in the Big Bang, performs a disappearing act that has puzzled cosmologists for decades. The theoretical framework we just explored, with its exquisite neutrino timing and fine-tuned baryon density, makes a crisp prediction. It forecasts that roughly 1 in every 10 billion primordial nuclei should be lithium-7. But when astronomers train their telescopes on the oldest stars in the Milky Way, the cosmic relics known as metal-poor halo stars, they find a stubbornly different story. These ancient suns, born from nearly pristine gas mere hundreds of millions of years after the Big Bang, carry the chemical fingerprint of the primordial fire. Their atmospheres are fossilized time capsules, preserving the very elemental mix that emerged from those first 3 minutes. And what they show is not a perfect match but a glaring shortfall. The observed lithium-7 abundance is barely a third of what the theory demands. It is as though a cosmic thief systematically erased 2 out of every 3 lithium atoms before the first stars ignited. This is no minor rounding error. The lithium problem represents the single largest unhealed crack in the armor of Big Bang nucleosynthesis. Think of it like a patient undergoing a full body scan. Every organ checks out perfectly. The heart of helium matches predictions, the bones of deuterium align with microwave background measurements, yet one stubborn joint, the lithium abundance, refuses to sit right. The discrepancy is too large to blame on measurement noise or simple telescope calibration. Astronomers have scrutinized dozens of ancient halo stars across our galaxy, and the pattern holds. Their lithium levels cluster at a value far below theoretical projections. Even more unsettling, the scatter among these old stars is remarkably small, hinting that a single primordial process imprinted the same deficit everywhere. This tension does more than tease scientists. It signals that a key ingredient in the cosmic recipe might be missing. The standard model is not necessarily wrong, but it might be incomplete. Perhaps the neutron lifetime measurements, a critical input to the calculations, harbor a hidden systematic error. Or maybe the cosmic microwave background radiation, our gold standard ruler of baryon density, has been subtly misinterpreted. But these fixes often create new problems, as if squeezing a balloon only to watch it bulge elsewhere. The real excitement lies in the possibility that the lithium shortfall is a messenger from new physics. What if dark matter particles were slowly decaying in the plasma, injecting energetic particles that shattered fragile lithium nuclei? What if a fleeting shift in fundamental constants, like the strength of electromagnetism, altered reaction rates just enough to burn away lithium? These are not wild fantasies but concrete hypotheses that link the lithium problem to the deepest unsolved mysteries of the cosmos. The data from metal-poor halo stars serve as the bedrock of this whole investigation. These stellar elders hover in the sparse outer halo of the Milky Way, and their surfaces show almost no elements heavier than helium because they formed before supernova had seeded the galaxy with iron and other forged metals. By measuring the absorption lines in their spectra, narrow dark bands where lithium atoms swallow specific wavelengths of light, scientists can calculate the primordial lithium abundance with remarkable precision. The technique is elegant but demands painstaking care. The stars must be old enough to avoid contamination from later generations, and their atmospheres must be stable enough to prevent lithium from sinking into the interior over billions of years. When these filters are applied, a consistent message emerges. The universe seemed to produce just 1/3 of the lithium that our best equations command. This stubborn mismatch has become the bedrock motivation for many of the wilder theories we are about to explore. Every alternative cosmology, every new particle, every exotic energy field that dares to rewrite the opening minutes must first stare down the lithium problem. It is the gatekeeper guarding the threshold of new physics. Solve it, and you might solve dark matter, the nature of gravity, or the hidden history of cosmic expansion. Leave it unaddressed, and your elegant model stumbles at the first hurdle. So as we journey deeper into the 30 theories that seek to explain the first light elements, remember that this single anomalous atom is the compass needle pointing beyond the known horizon, daring us to follow. The cosmic soup was never a perfectly still, uniform broth. A radical departure from the smooth standard model imagines the early universe as a churning, lumpy cauldron, where dense knots and thin voids could have rewritten the story of the first light elements. This is the theory of inhomogeneous nucleosynthesis, and it begins not with particles but with a cosmic phase change. In the very first microseconds after the Big Bang, the universe was so hot that protons and neutrons could not even exist. Instead, their building blocks, quarks and gluons, swirled freely in a state known as a quark-gluon plasma. As expansion cooled this ocean below trillions of degrees, the quarks abruptly froze into the protons and neutrons we know today. That transition was no gentle sunset. It may have been a violent churning event like water flash freezing into ice. And just as freezing water can trap air bubbles in irregular pockets, the quark-hadron phase transition might have seeded the infant cosmos with dense knots of matter floating in expanses of emptier space. These were not the vast galaxy clusters we see today, but microscopic density fluctuations, regions where the local ratio of neutrons to protons strayed far from the cosmic average. In a smooth universe, the neutron-to-proton ratio is a single universal melody, the same fractional note everywhere. But in a clumpy universe, each pocket becomes its own distinct instrument. Some regions emerged from the quark transition with a neutron surplus, perhaps because the strange physics of quark confinement allowed neutrons to gather more readily in high-density zones. Others became neutron deserts dominated by lone protons. As the universe continued to expand and cool through the crucial 3-minute nucleosynthesis window, these pockets did not instantly mix. They remained chemically isolated for precious moments, allowing different nuclear recipes to cook in parallel. This is the heart of inhomogeneous nucleosynthesis, a scenario where the universe is not a single standard kitchen, but a sprawling neighborhood of tiny specialized eateries, each plating a slightly different elemental menu. The most fascinating consequence swims around the lithium problem. Recall that the standard model overproduces lithium-7 by a factor of 3 compared to what ancient halo stars display. In a lumpy cosmos, the neutron-rich pockets become lithium wrecking yards. With extra neutrons available, a side channel of nuclear reactions could have burned lithium-7 into beryllium-7, which later decayed into lithium-7, but along a different path that might net out to less final lithium. More importantly, free neutrons themselves could have slammed directly into fragile lithium-7 nuclei, shattering them into smaller fragments like a demolition crew. Meanwhile, in the neutron-poor regions, the scarcity of building blocks suppressed lithium production from the start. The overall universe-wide average could then mask a radical spatial variation, a patchwork where some zones had their lithium erased while others barely formed any at all, blending to produce the low average we observe today. The quark-hadron phase transition acts as the cosmic seed drill in this narrative. The physics of that transition remains fiercely mysterious because we cannot recreate those energies in any laboratory on Earth. Theorists must rely on supercomputer simulations to model how quarks behave when they are suddenly locked into cages of larger particles. The results hint that the transition was a violent birth, akin to steam bubbles collapsing in a boiling pot. Shockwaves and expanding shells could have swept neutrons into concentrated drifts while protons were pushed the opposite way. This separation, operating on scales of a few meters but stretched by cosmic expansion to stellar scales, would have imprinted the element-building era with a hidden geography. It is a tantalizing vision because it solves the lithium shortfall not by tweaking particle physics, but by changing the very landscape of the early fireball. Yet the theory stumbles on a harsh reality, the perfection of helium and deuterium. The standard smooth model nails their abundances with breathtaking precision, matching observations from pristine gas clouds and the cosmic microwave background to within a few percent. An inhomogeneous universe is a messy chef. Those neutron-rich pockets that burn lithium-7 also massively overproduce helium-4 because more neutrons inevitably forge more helium. Even small density lumps inflate the helium abundance beyond what ancient stars allow. Simultaneously, the deuterium bottleneck, that fragile balance of destruction and survival, gets thrown into chaos. In neutron deserts, deuterium would be even harder to build, while in neutron-rich zones it would be crushed into helium so efficiently that the overall deuterium signature no longer aligns with the exquisite measurements from distant quasars. The theory, while elegant, ends up trading one anomaly for a swarm of new discrepancies. Researchers have run exhaustive grids of models varying the density contrast, the size of the pockets, and the speed of mixing. The verdict is blunt. The universe can be a little lumpy and still satisfy helium and deuterium constraints, but it cannot be lumpy enough to erase the lithium problem without spoiling the rest. Any scenario that slashes lithium-7 by the required factor overshoots helium-4 or throws deuterium off by a mile. The window that works for all three elements is vanishingly small, much too narrow for the rough and tumble physics of a quark-hadron phase transition to hit by chance. This does not kill the idea of a textured early cosmos entirely. It simply means that pure neutron pocket models cannot stand alone as the solution. Perhaps the fluctuations were not in baryons, but in exotic dark matter decaying at just the right rate. Or maybe the phase transition was gentler, leaving behind only the faintest whispers of structure that a future generation of telescopes could detect in the cosmic microwave background. The legacy of inhomogeneous nucleosynthesis endures because it forces us to confront the deep assumption of a featureless beginning. It whispers that the cosmic dawn was a storm, not a still pond, and that the true solution to the lithium puzzle might merge this storm geography with the hidden particle physics we have yet to map. As our exploration of the 30 theories deepens, keep this lumpy vision close, because it will surface again when we consider exotic dark matter decays and bouncing universes that may have shaken the primordial cauldron more violently than we ever imagined. A hidden family of particles could have staged a delayed chemical attack on the infant universe. This theory dips into the strange realm of supersymmetry, a grand mathematical framework that doubles the particle zoo of known physics. For every familiar particle like an electron or a quark, supersymmetry proposes a heavy mirror twin, a partner that has eluded our detectors but may have teemed in the blistering heat of the Big Bang. Many of these superpartners are violently unstable, crumbling almost as soon as they form, but a select few, such as the gravitino and the neutrino, might have clung to existence for hours, days, or even centuries after the primordial fire dimmed. Their secret role was not to build the first light elements, but to vandalize them long after the standard kitchen had closed. The key to this cosmic sabotage lies in timing. Standard nucleosynthesis ran its course in roughly 3 minutes, locking hydrogen, helium, deuterium, and lithium into a fixed census. Then the universe expanded, cooled, and went quiet. If a population of long-lived superpartners had lurked in the cooling plasma, they would have bided their time while the ordinary nuclear reactions froze. Only later, when the cosmos had stretched far and cool, would these heavy particles begin to lose their grip on existence. A gravitino, for example, is the hypothetical superpartner of the graviton, the carrier of gravity. It interacts so faintly that it could drift unbothered through the thinning fog, its internal clock ticking slowly. After the standard element building was long over, a single gravitino could suddenly decay, bursting into a shower of energetic photons or a spray of hadrons, the particles that feel the strong nuclear force. That injection lands like a delayed bomb in the freshly forged nuclei. Photodisintegration is the elegant term for what follows. A high-energy photon smashes into a fragile lithium-7 nucleus with enough force to pry it apart. The tightly bound helium-4 nucleus can endure these late hits with remarkable stoicism, its sturdy frame absorbing blows without shattering. But lithium-7 sits precisely on the knife edge of nuclear stability. A well-tuned photon can cleave it into lighter fragments, such as helium-4 and a tritium nucleus, effectively erasing the lithium from the ledger. This is the delicate magic that theorists have seized upon. The standard model overproduces lithium-7 by a stubborn factor of 3. But if a drizzle of decaying superpartners smashed just the lithium after the main cooking was done, the final tally would drop without disturbing the pristine abundances of helium and deuterium that they had already gotten so perfectly right. Even more clever, this destruction leaves a calling card. Hadronic showers, those sprays of particles like pions and protons triggered when a neutrino or gravitino decays, do not just break things. They also stitch new nuclei together through secondary collisions. The most telling fingerprint emerges in lithium-6. Standard cosmology barely makes any lithium-6, predicting a vanishingly tiny primordial supply. But when hadronic showers tear through a quiet gas of helium-4, they can fuse helium nuclei into lithium-6, beryllium, and other rare species. A sharp spike in lithium-6, precisely the element that was never supposed to be there, would be the smoking gun of a post-nucleosynthesis particle assault. Observing an ancient star with an anomalously high lithium-6 to lithium-7 ratio would light up physics departments around the world, because it could not be explained by a smooth cosmic kitchen or even by lumpy quark bubbles. It would be the unmistakable signature of something surviving long after the first 3 minutes. This makes the scenario exquisitely testable. Astronomers have already trained their spectrographs on metal-poor halo stars to hunt for this exact lithium-6 excess. The early results, while not yet definitive, have placed powerful constraints. The amount of energy that decaying particles could have dumped is heavily policed by the cosmic microwave background, because late injection of photons and electrons would have distorted that pristine glow in ways we do not observe. Any surviving superpartner is therefore boxed into a tight corner. It must be heavy enough with a mass above a few tera electronvolts to decay with sufficient punch. It must be long-lived but not immortal, its lifetime threaded through a narrow needle eye that lets nucleosynthesis finish before the assault begins. And it must be abundant enough in the early moments to matter. yet must vanish so cleanly that it does not clutter the modern universe in a way that contradicts searches at the Large Hadron Collider or in deep underground dark matter detectors. The neutrino stands as a favorite candidate in this drama. In many versions of supersymmetry, the neutrino is the lightest superpartner and is absolutely stable, forming the dark matter that suffuses galaxies today. But in a variant called R-parity violating supersymmetry, this stability breaks and the neutrino decays slowly into ordinary particles. A decaying neutrino could thus bridge the dark matter mystery and the lithium problem in a single breathtaking stroke. It would mean that the very substance holding the Milky Way together was once busily pruning lithium atoms in the cosmic nursery. The same philosophical sweep applies to the gravitino. In theories where the gravitino is the lightest superpartner, its decay is governed by gravitational strength, making its lifetime naturally long. It could drift across the minutes like a slow-burning fuse, then light up the expanding cloud with a soft, destructive glow that selectively erased the troublesome lithium. Of course, the path is tight and riddled with pitfalls. To slash lithium 7 by 60% without touching deuterium demands pinpoint precision. If the photon energy is too high, it shatters deuterium with equal ease, creating a new discrepancy. If the hadronic shower is too dense, it overproduces lithium-6 to levels that would have been easily spotted by now. The theory is not a blunt hammer. It is a surgical scalpel that must operate on a patient spread across billions of light years, guided only by the faint fossil records in dying stars. Researchers build intricate computer models, tracking the cascade of particles as they bounce and breed in the cooling gas, adjusting the mass, lifetime, and abundance of the decaying sleeper particle to hunt for that magical combination that fixes lithium 7 and 6 simultaneously without breaking anything else. The fact that this solution threads through the most profound unsolved problem in particle physics, the nature of dark matter, gives it an irresistible allure. It whispers that the lithium shortfall is not a mistake to be ironed out with better telescope calibration, but a genuine relic of the unknown sector, a chemical photograph of particles that once held dominion over the early universe and then vanished. As our cosmic detective story unfolds, keep your eye on this unusual suspect. The faintest ghost of lithium-6 in a distant halo star could one day shatter our entire understanding of the dark side of creation. Among the strangest phantoms that might have haunted the early fire are not particles at all, but vanishing knots of gravity. Tiny black holes, born in the first moments, could have flickered and died as the universe wove its first atoms. Unlike the stellar monsters that collapse from dying stars, primordial black holes would have been forged directly from the crushing squeeze of the infant cosmos itself. In the merest slivers of a second after the Big Bang, space was stretching so violently that random pockets of energy could collapse under their own weight, pinching off into microscopic black holes no larger than an atomic nucleus but packing the mass of a mountain. These were not stable relics. Stephen Hawking taught us that black holes are not perfectly dark. They slowly leak energy through a quantum trick at their boundary and grow hotter as they shrink. The smallest ones evaporate fastest, vanishing in a brief, brilliant flash of escaping particles. For a certain mass range, those final moments would arrive right in the middle of the nucleosynthesis era, precisely when the cosmos was stitching its first light elements. A primordial black hole with the right birth weight, perhaps 1 billion metric tons, could smolder through the first minutes before detonating into a spray of photons, electrons, and even heavy quarks, dumping a sudden spike of energy into the cooling broth. This delayed heat injection would act like a tiny blowtorch in an otherwise uniform kitchen. Local pockets of space, especially if many black holes were clustered together, would be briefly reheated. That thermal jolt could knock the delicate reaction rates off balance just enough to shift elemental abundances. The deuterium bottleneck, so sensitive to temperature, might be loosened a whisper earlier in those hot spots, altering how efficiently deuterium got burned into helium. At the same time, the high-energy photons streaming from the evaporating black hole could hunt down fragile lithium-7 nuclei and break them apart, much like the decaying particle scenario, but powered by the dying gasp of gravitational singularities. The most tantalizing version of this hypothesis imagines that the cosmos was not seeded with a smooth sprinkling of these objects, but with dense clumps of them, entire swarms of evaporating black holes acting in unison. In those clustered regions, the combined radiation pressure might have been enough to sculpt the surrounding plasma, creating fleeting chemical shelters where lithium was systematically pruned while helium and deuterium marched on nearly untouched. This would mean that the lithium shortfall we measure in ancient halo stars is not a universal erasure, but an average drawn from a patchwork of black holes, scoured zones, and quieter stretches, a subtle geography imprinted by gravity's tiniest monsters. The idea is breathtakingly bold, but it also runs straight into an observational wall of light. The universe today is remarkably dim in gamma rays. If swarms of microscopic black holes had evaporated during the Big Bang's first few minutes, they would have left behind a faint but unmistakable glow, a diffuse gamma-ray background that modern telescopes like the Fermi Large Area Telescope can measure with exquisite sensitivity. Even if the black holes popped off in the very early universe, the redshifted relic radiation would persist as a soft bath of high-energy photons filling intergalactic space. The most rigorous surveys find no such excess, which tightly fences in how many of these objects could have existed. Generally, the data permit only a vanishingly small fraction of the cosmic dark matter to have taken the form of primordial black holes that evaporated during nucleosynthesis. Too many, and the gamma-ray signature would shout through the centuries of cosmic expansion. Furthermore, the mass window that allows evaporation during the element-building minutes is narrow and exquisitely tuned. A black hole slightly heavier would live too long, decaying after the relevant reactions were frozen. A slightly lighter one would burst too early, before the standard nucleosynthesis had even set the table. And the energy spectrum of Hawking radiation is a democratic torrent of all particle species, not a single surgical beam. Alongside the photons that might erase lithium, the black hole would also spray out electrons, muons, and pions that could shatter deuterium or overproduce lithium-6 to levels that ancient stars do not show. So the scenario, much like the decaying superpartner idea, must thread a needle so fine that few theorists feel it can hit the bullseye by chance alone. Yet the concept refuses to die because it links three profound mysteries in a single framework: the lithium problem, the nature of dark matter, and the quantum face of gravity. Even if primordial black holes cannot solve the lithium riddle by themselves, their fleeting presence might have blended with other new physics to produce the exact element cocktail we observe. Every constraint from the gamma-ray sky yields a clearer map of what could have been, steadily eliminating mass ranges and cluster densities until only the most hidden possibilities remain. And that is the quiet promise behind this strange idea. It reminds us that the cosmic oven may have been far more turbulent and inventive than a single smooth recipe, and that the true solution to the lithium anomaly might lie not in a new particle but in the violent death of objects whose whole existence is a ghost story whispered by general relativity. The search for their faint gamma-ray afterglow continues, and with every dark patch of sky we learn a little more about the monsters that might have danced in the light of creation's first minutes. Even the deepest laws of physics may have drifted in the heat of creation. The notion that the fundamental constants of nature are carved immutably into the fabric of reality is a cornerstone of modern science. Yet a daring strand of cosmology suggests that in the blistering opening minutes, the very rules of the game were still finding their footing. The fine structure constant, often called alpha, governs the strength of electromagnetism. It is a pure number, roughly 1 divided by 137, and it controls how firmly atoms hold onto their electrons and how fiercely charged particles repel or attract. The proton-to-electron mass ratio is another dimensionless pillar, set near 1836, determining the scale of all atomic structure. If either of these numbers had been subtly different when the first nuclei were stitching together, the entire elemental cocktail would have been stirred into a new recipe. In the standard cosmic kitchen, these constants are treated as eternal and unchanging. The fusion of protons and neutrons into deuterium depends exquisitely on the exact binding energy of that fragile nucleus. Even a whisper of a change in the electromagnetic force would alter the depth of the deuterium bottleneck, letting it survive at slightly higher or lower temperatures, and thus shifting how much helium, lithium, and deuterium ultimately emerge. A slightly stronger alpha would make protons repel each other more fiercely, making it harder for fusion to proceed until the universe cooled further, potentially leaving more leftover deuterium and less helium. A slightly weaker alpha would grease the nuclear gears, burning deuterium faster and bloating the helium abundance in ways that clash with observations of pristine gas clouds. This is not merely a philosophical meditation. It opens a direct avenue to measure the unmeasurable. The cosmic microwave background and the chemical fossils in ancient halo stars serve as exquisitely calibrated thermometers and clocks. If nature had tinkered with alpha by even a few parts in a million during nucleosynthesis, the predicted ratios of light elements would shift, and the beautiful agreement between theory and observation for helium and deuterium would splinter. Theorists have run painstaking simulations that tweak these constants inside computer models of the Big Bang, searching for a new sweet spot where all three abundances match reality. The results are sobering. Changing alpha by more than 1% generally shatters the helium match, while smaller shifts leave the stubborn lithium discrepancy untouched. The lithium problem is particularly sensitive to the proton-to-electron mass ratio because the rates of key reactions, especially those involving beryllium-7 that later decays into lithium, pivot on the precise masses of the players. A drift in that ratio during the first minutes, perhaps driven by a coupling to a rolling scalar field that later froze into its present value, could have trimmed lithium production while sparing the sturdier nuclei. The idea that the constants might have wandered in the early universe ties directly to observations of distant quasars. These brilliant cores of ancient galaxies shine their light across billions of years, and the gas clouds in between absorb that light at specific wavelengths. By comparing the atomic fingerprints imprinted on quasar spectra with the same fingerprints measured in laboratories on Earth today, astronomers can detect whether the fine structure constant was different when the universe was a fraction of its current age. Some research teams, like the one using the Very Large Telescope in Chile, have reported tantalizing hints that alpha was slightly smaller in the distant past, a variation of a few parts in a million. Other surveys using more remote quasars and different methods find no variation at all, setting ever tighter upper limits. This ongoing tug-of-war is one of the most thrilling frontiers in fundamental physics. The lithium anomaly adds a unique twist to this search. If a slight diminution of alpha or a gentle nudge in the mass ratio occurred specifically during the first 3 minutes, it could have left the lithium abundance we see today as its sole survivor. But that variation would have to vanish afterward, locking into the stable values we measure now, a temporal tightrope act that demands a new kind of dynamic field, often called a quintessence field, which changes over cosmic time. In such scenarios, the constants are not fixed by divine decree, but are the equilibrium points of a deeper, evolving vacuum. The early universe was hotter and denser, and the very structure of space-time may have been different enough to shift these numbers. As the cosmos cooled, the field settled, freezing the constants at their present values, leaving us with a universe that just happens to be fine-tuned for stars, planets, and observers. This idea is not without its own challenges. Any variation strong enough to erase lithium must not ruin the precise match of deuterium and helium, which requires an almost miraculous cancellation of effects. Moreover, the same quintessence field that alters nuclear reactions would also modify the expansion rate of the early cosmos, which in turn changes the cosmic microwave background fluctuations in ways that the Planck satellite's exquisite maps would detect. The data currently favor constancy, but the search continues at ever finer precision. Each photon from a distant quasar is a letter from the ancient cosmos, and every spectrum analyzed either tightens the noose on varying constants or cracks open the window to new physics. The lithium problem remains the silent partner in this investigation, reminding us that one of the fundamental dials of reality might have turned ever so slightly during the first flicker of cosmic time, reshaping the atoms that would one day compose galaxies, stars, and the very hands that scribble down equations on a chalkboard. Beyond drifting constants, another hidden architecture may have shaped the first atoms. A secret twin to our entire material world could be hiding in plain sight, a mirror sector of particles and forces nearly identical to our own, yet invisible to every sense except the faint pull of gravity. This is not a fantasy of science fiction, but a rigorous hypothesis born from the symmetries that already govern particle physics. The standard model of particle physics is built on deep mathematical mirrorings where certain transformations leave the fundamental equations unchanged. Theorists have long wondered whether nature doubled down on this symmetry, crafting an entire parallel set of particles, mirror electrons, mirror protons, mirror neutrons, and even mirror light, that coexist with us in the same space but interact only through the gravitational handshake that everything feels. Imagine two vast audiences sitting in the same darkened theater, each watching a different film projected on the same screen, completely unaware of the other crowd because they cast no visible shadow. That is the ghostly existence of a mirror sector. It does not reflect our familiar electromagnetic or nuclear forces, meaning mirror atoms cannot shine, collide chemically, or build stars in any way we can directly see. Yet they would still tug on the fabric of space-time, and that subtle pull is why the idea has earned such serious attention from cosmologists hunting dark matter. If the mirror sector exists, it could account for the invisible mass scaffolding galaxies, making it a prime candidate for the cosmic dark side. The real twist for our story of the first light elements lies not in the bulk mirror matter, but in a tiny, almost imperceptible crack in the wall between the two worlds. Physicists call it mixing, a quantum loophole that allows certain particles to very occasionally flit across the boundary and swap identities with their mirror twins. For nucleosynthesis, the crucial actor is the neutron. In our world, the neutron is slightly heavier than the proton, and when free, it decays in about 15 minutes. In the mirror sector, a mirror neutron would presumably have similar properties, governed by mirror versions of the strong and weak nuclear forces. If a minuscule mixing term links the two, then an ordinary neutron traveling through space could spontaneously oscillate into a mirror neutron and back again, as if it were a shape-shifter slipping between two dimensions. This oscillation is not a slow drift but a fleeting quantum beat, where the neutron exists in a superposition of being both ordinary and mirror at the same time, with its true nature only revealed by how it interacts. In the fiery broil of the early universe, such oscillations would have rewritten the neutron budget, the total count of free neutrons available to cook the first elements. The effect is subtle but surgical. As the primordial soup expanded and cooled through the crucial first minutes, neutrons were constantly trying to lock themselves into deuterium and then helium, all while racing against their own internal decay clock. If a fraction of those neutrons kept vanishing into the mirror sector, becoming mirror neutrons that no longer participate in ordinary nuclear reactions, then the effective neutron density was lower than cosmologists assumed. Fewer neutrons means less helium-4 gets forged, because helium-4 is the ultimate neutron sponge. each nucleus gobbling up 2 neutrons. This could nudge the predicted helium abundance gently downward, which at first sounds like a problem because the standard model already matches helium so perfectly. But remember, the helium match is not rigid. There is a small but real window of allowed abundance, and some astronomical measurements of pristine gas actually favor a slightly lower helium mass fraction than the central theoretical value. A modest rate of neutron-to-mirror neutron oscillations could ease the helium prediction into even sweeter alignment with these lower estimates. More critically, the oscillation rate can be tuned with remarkable precision. The mixing strength is not an arbitrary dial. It is a physical parameter rooted in the energy scale of whatever new physics bridges the two sectors. The same neutron oscillations that deplete the ordinary neutron supply leave a complementary signature in the deuterium abundance. Since deuterium is built from 1 proton and 1 neutron, a reduced neutron density relaxes the crunch to form it. That slightly alters how much deuterium survives the bottleneck, but because deuterium is exquisitely sensitive to the baryon density we already measure from the cosmic microwave background, any shift here must be gentle. Theorists have mapped the interplay between the oscillation rate and the expansion of the universe, finding narrow corridors where both helium and deuterium stay within their observed bounds while the mirror losses actually improve the overall fit. And then we arrive back at the lithium problem. A depleted neutron supply during nucleosynthesis might trim lithium-7 production indirectly because the complex chain that ends in lithium depends on the ratio of neutrons to protons and the temperature at which key beryllium reactions freeze out. If fewer neutrons were rattling around, the pathways that build beryllium-7, which later decays into lithium, can be slightly suppressed. This does not cleanly erase the full factor of 3 lithium shortfall by itself, but it can contribute a piece of the puzzle, reducing the lithium yield by a few tens of % without spoiling anything else. The real power of the mirror neutron oscillation scenario is that it provides a coherent, testable framework that connects the early universe to the modern dark matter mystery. The same mirror sector that subtly tweaked element abundances is the one whose mirror atoms might still be drifting through the galaxy as dark matter. And unlike many speculative theories, this one offers a concrete experimental handle. Laboratories on Earth have attempted to directly measure neutron-to-mirror neutron oscillations by sending beams of ultra-cold neutrons through shielded vacuum chambers, watching for any that inexplicably vanish and reappear. If a neutron flips into a mirror neutron, it would simply disappear from the ordinary detector, leaving a detectable absence. So far, these experiments have set tight upper limits on the mixing strength, restricting it to timescales longer than hundreds of seconds. That is enough room to still play a role in the Big Bang because the universe provided a vast number of neutrons across cosmic time, and even a slow oscillation rate would have processed a meaningful fraction. Another pillar of support comes from the cosmic microwave background. The mirror sector, if it had even a tiny temperature relative to our own, would act as an additional source of radiation energy in the early universe, speeding up cosmic expansion slightly. This extra radiation density, often parameterized by the effective number of neutrino species we discussed earlier, is rigorously constrained by the Planck satellite's maps of the primordial glow. If the mirror sector was too warm, it would overproduce helium by altering the freeze-out timing, exactly the opposite of the desired effect. So the mirror sector must have been born cold, thermally disconnected from our own from the very start, perhaps seeded by its own separate inflation or by the asymmetric decay of a parent field. In that cold mirror scenario, the relic mirror neutrons that survive today could be the primary component of dark matter, a ghostly ocean of particles that feels only gravity and the faintest whisper of quantum mixing. The elegant thread stitching this all together is that the same tiny portal that explains the lithium and helium abundances may also one day be discovered in a quiet underground laboratory, when a neutron beam mysteriously dims as a few of its members step silently through the mirror. It is a hypothesis that elevates the first 3 minutes from a closed historical chapter into an ongoing experiment, with every ancient halo star and every trapped ultra-cold neutron acting as dual witnesses to a grander, doubled creation. But what if dark matter did not just drift silently through the early fire? Some particles may have smashed into each other and vanished, leaving behind a searing spray of energy that rewrote the recipe for the first light elements. This is the theory of dark matter annihilation during nucleosynthesis, and it weaves the cosmic dark matter mystery directly into the fabric of the element puzzle. Unlike the long-lived decaying particles we explored earlier, these dark matter particles were not waiting to crumble on their own. They were actively hunting one another in the dense, hot plasma, and when they met, they transformed their entire mass into a burst of photons, electrons, or neutrinos. That injection of pure energy, arriving in the delicate minutes when nuclei were taking shape, could have acted like a hidden thermostat, a silent accelerator, or even a demolition crew. The most studied candidates for this role belong to a class called weakly interacting massive particles, or WIMP. In many theories, these particles are their own antiparticles, so whenever two of them drift too close in the dense early cosmos, they can annihilate instantly, converting their combined mass into a flash of standard model particles. The rate at which this happens depends exquisitely on how crowded the universe was and how the annihilation cross-section behaves with temperature. A subtle detail known as P-wave suppression becomes crucial. Many WIMP models predict that their annihilation slows to a crawl at low temperatures when particles are moving more sluggishly. This means they barely touch each other in the cold, empty universe of today, avoiding a glaring glow of modern gamma rays that telescopes would have already spotted. But in the blazing furnace of the Big Bang's first minutes, when particles rocketed through the plasma, that suppression was lifted. They could annihilate furiously right when the standard element factory was running, then fall silent as the cosmos cooled, leaving only the fossilized light elements as evidence of their rampage. The energy dumped by these annihilations could have reshaped the primordial kitchen in 3 interconnected ways. First, it could have tweaked the cosmic expansion rate. By injecting an extra splash of radiation, dark matter annihilation would have added energy to the photon and neutrino soup, nudging the universe to expand a little faster during the nucleosynthesis window. A faster expansion shifts the delicate timing of the deuterium bottleneck and the freeze out of the weak interactions, changing the exact moment when neutrons and protons stopped converting into one another. That subtle shift can dial the neutron-to-proton ratio up or down, subtly altering the final yields of helium and deuterium. Second, the injected energy could have acted as a local heat source, briefly reheating pockets of the cooling plasma and delaying the moment when nuclei could finally hold together without being shattered by ambient photons. This thermal bump would especially affect fragile deuterium, which is notoriously easy to destroy, potentially leading to a slightly different survival pattern. Third, and most directly, the annihilation products could have smashed into already formed nuclei. A spray of high-energy photons can trigger the same kind of photodisintegration we met in the decaying particle scenarios, breaking apart lithium-7 nuclei into lighter fragments. Simultaneously, sprays of electrons and neutrinos could nudge reaction rates in unexpected ways, such as boosting the conversion of neutrons to protons, which shifts the foundations on which all subsequent nuclear cooking is built. This is the deep allure of connecting dark matter annihilation to the light element puzzle. It means the same hidden substance that holds galaxies together might have quietly trimmed the lithium abundance while gently massaging the helium and deuterium predictions to stay within their tight observational bounds. The great challenge is that the cosmic microwave background acts as a strict overseer. Any energy injection during nucleosynthesis also left a mark on the pattern of hot and cold spots in that ancient light. By annihilating into charged particles or photons, dark matter would have skewed the ionization history of the universe, leaving a detectable distortion that the Planck satellite and other experiments have carefully searched for. The resulting limits are severe. The amount of energy that could have been dumped is so tightly constrained that only a sliver of annihilation parameter space remains viable. For instance, if dark matter annihilated mostly into neutrinos, which escape the plasma without distorting the microwave background as strongly, the bounds relax somewhat, offering an open window. Models where the annihilation was strongest during the exact few minutes of nucleosynthesis, then shut off completely, can also thread this needle by leaving the later cosmic epochs untouched. This requires a delicate balancing act, often pointing to dark matter candidates with unusual properties, like a resonant annihilation channel that activates only in a narrow temperature range. The lithium problem once again stands as the pivot. Fitting all the light elements simultaneously is like solving a multidimensional puzzle where every knob, the dark matter mass, the annihilation rate, the fraction of energy going into hadrons versus leptons must be set just right. Researchers have run extensive grids of computer models that simulate the entire first hour of cosmic history with annihilating dark matter included. They find that certain configurations can slash the predicted lithium-7 abundance by a significant fraction, perhaps not the full 60% needed, but enough to offer a crucial piece of the solution. The remaining shortfall might then be explained by a complementary effect, such as the mirror neutron losses we discussed, or by yet another layer of new physics. What makes this avenue so compelling is that it connects two of the grandest unsolved mysteries in science. The nature of dark matter and the origin of the first light elements become intertwined, so that solving one might spontaneously illuminate the other. Imagine a future where a dark matter detection experiment deep underground finally catches a particle, revealing its mass and interaction strength, and those same numbers, plugged into a Big Bang nucleosynthesis code, automatically fix the lithium anomaly that has haunted astronomers for decades. That would be a unification of cosmic scales from the subatomic to the galactic that few other theories can offer. The laboratories hunting for dark matter today, such as massive liquid xenon tanks or ultra-sensitive cryogenic crystals, are therefore not just chasing an invisible substance. They are also probing the very forges that crafted the atoms in your body. Each null result, each tightening of the upper limit on the WIMP annihilation cross-section, acts as a new constraint on the primordial kitchen, narrowing the range of viable models and sharpening the questions. Meanwhile, the James Webb Space Telescope and the next generation of extremely large ground-based observatories are finding ever more pristine ancient stars, whose chemical fingerprints can test the predictions of these annihilation scenarios in exquisite detail. If one of those stars were to show a faint but distinctive spectral signature of a beryllium or lithium isotope ratio that only energetic particle injection can produce, it would be the proverbial smoking gun. So the dark matter annihilation theory lingers at the frontier, not yet vindicated but far from abandoned. It serves as a powerful reminder that the darkness between the stars is not a void but a closet of hidden physics, and that the opening minutes of creation might have been far more crowded and creative than a simple smooth recipe allows. As we venture further into the list of 30 theories, keep hold of this image of a seething dark sector, not just silently warping space-time, but actively cooking, burning, and sculpting the very elements that would one day compose the first stars and the first life. A particle even more elusive than dark matter might have raced through the early cosmos. The sterile neutrino is a true ghost among phantoms, a hypothetical cousin to the familiar neutrino that feels nothing but the distant tug of gravity. While ordinary neutrinos occasionally bump into electrons or atomic cores through the weak nuclear force, a sterile neutrino would slide through solid lead, through planets, through entire stars without leaving a single trace. It lives entirely in the dark, never emitting light, never scattering off protons, never joining the nuclear dance that builds the visible world. And yet its existence would have been anything but silent during the first 3 minutes. The presence of even one additional sterile neutrino would have shifted the very rhythm of cosmic expansion, leaving a permanent chemical signature written across every atom of helium and deuterium forged in that ancient furnace. The core effect is beautifully simple. In the infant universe, every type of particle that moved at or near the speed of light contributed to the total radiation energy density. Photons, the 3 known flavors of neutrinos, and any extra relativistic species all acted like a single invisible spring, pushing space apart faster. We measure this radiation density with a number called the effective number of neutrino species, which the standard model pegs at just over 3. Add a sterile neutrino and that number jumps. Add 2 and it climbs further. A higher radiation density means the universe expanded more rapidly during the crucial weak interaction freeze-out, the moment when protons and neutrons stopped swapping identities and their ratio became locked in stone. That 1-second-old freeze-out was the foundational snapshot we explored earlier. If the cosmic clock was ticking faster, the freeze-out happened at a slightly higher temperature. A hotter freeze-out preserves a higher fraction of neutrons because the balance tilts ever so slightly against the lighter proton. That surplus of neutrons, in turn, cascades directly into the final yield of helium-4. Each helium-4 nucleus is a neutron sponge soaking up 2 neutrons, so more neutrons simply means more helium. The shift is a razor-sharp prediction. A single extra sterile neutrino would inflate the primordial helium-4 mass fraction by nearly a full percentage point, a massive change for a measurement that astronomers have nailed to within fractions of a percent. This is not a subtle nudge, but a loud, clear signal that telescopes can directly verify or falsify. And this is where the sterile neutrino becomes a scouting probe into the uncharted territory of particle physics. Observations of the most pristine gas clouds in the distant universe, those untouched by generations of starlight, have returned helium-4 abundances that cluster tightly around the standard model's prediction. The wiggle room is small but not zero. Some measurements nudge slightly higher, others slightly lower, and the uncertainty leaves a narrow corridor where one sterile neutrino could still hide. However, if a second sterile neutrino had joined the primordial party, the helium-4 production would overshoot the observed values so brazenly that the idea would be ruled out. The standard cosmological kitchen, therefore, places a strict upper limit on how many of these ghostly species could exist. At most, one fully thermalized sterile neutrino might have been present. This makes every improved measurement of ancient helium a direct test of the most elusive particles in nature. The story grows richer when we consider that sterile neutrinos need not be fully thermalized to leave their mark. They might have been born cold, produced only partially through subtle quantum mixing with ordinary neutrinos. In that case, their impact on the expansion rate is diluted, allowing them to slip under the helium constraints while still contributing to the total radiation energy. This partial mixing opens a path to addressing the lithium problem indirectly. A slight upward nudge in helium-4, combined with the other physics we have discussed, could shift the entire predicted elemental cocktail in ways that improve the overall fit to ancient stellar data. The sterile neutrino then becomes part of a symphony, not a solo instrument. The hunt for these hidden particles spans both the heavens and the Earth. Laboratory experiments like the short baseline neutrino program at Fermilab fire beams of neutrinos through detectors, searching for the telltale oscillation signature that would reveal a sterile partner. Meanwhile, satellite observatories like Planck have meticulously mapped the cosmic microwave background, and their maps are exquisitely sensitive to the early expansion rate. Any extra radiation, whether from sterile neutrinos or any other hidden species, would have subtly altered the pattern of hot and cold spots imprinted on the primordial glow. The Planck data, combined with the chemical fossils in ancient stars, have squeezed the effective number of neutrino species down to a value remarkably close to 3, with only a whisper of room for anything extra. The latest fits from the most comprehensive cosmological surveys suggest the number sits near 2.8, tantalizingly below the standard 3, though the error bars still encompass the possibility of a small sterile contribution. This means the cosmos is daring us to push further, to build more sensitive detectors, to find more pristine stellar fossils, and to map the microwave sky with even finer needles. A discovery of a sterile neutrino would crack open a hidden sector of reality, revealing a whole new family of particles that interact only through gravity. It would mean that the standard model, for all its triumphs, is missing entire categories of matter, and it would tie back to the very first minutes, proving that the early universe was a laboratory dense enough and hot enough to forge not just the light elements, but also the faint fingerprints of physics beyond our current dreams. Every helium atom that drifts in an intergalactic cloud is a recorded vote cast in that ancient referendum on the number of neutrino species. We are still counting those ballots, one spectral line at a time. A web of surgical scars thinner than an atom yet stretching across the sky may have sliced through the newborn universe. The violence of cosmic birth was not limited to quarks freezing into protons or particles blinking into existence. It may also have fractured space itself. In the very first fractions of a second, the universe underwent a series of wrenching phase transitions, moments when the fundamental forces of nature peeled apart from a single unified superforce. Just as a pond freezing over can trap cracks and fissures in the ice, the rapid cooling of the cosmos could have left behind permanent defects in the fabric of spacetime. These were not mere cracks in the stuff within space, but stable, vibrating fractures of space itself. Cosmologists call them topological defects, and the most captivating among them is the cosmic string. Think of it as a wrinkle left over from a more symmetric era, a filament of concentrated energy where the vacuum of space has not fully settled into its modern form. A cosmic string born in the electroweak phase transition, the moment when electromagnetism and the weak nuclear force separated, would be an astonishingly thin yet immensely heavy relic, with a width far smaller than a proton but a mass that could rival a mountain compressed into every meter of its length. These strings would not sit still. Formed in a tangled, chaotic network, they would thrash and oscillate at nearly the speed of light, whipping through the early universe like snapped power lines. As they writhed, they would ring, radiating their titanic energy outward in two distinct forms that both bear directly on our mystery of the first light elements. The first is gravitational radiation, ripples in spacetime that would have streamed from every flickering loop and kink in the string network. The second, and far more crucial for nucleosynthesis, is the possibility that these strings could also spray out high-energy particles. When two segments of a cosmic string cross, they can undergo a process called intercommutation, snapping and reconnecting into new sharp-edged configurations. At the cusps and kinks where the string turns almost instantly, the titanic energy density can become so concentrated that the string effectively unravels into a shower of ordinary particles, a burst of photons, electrons, quarks, and neutrinos erupting from the pure geometry of bent space. These bursts would not have been gentle. A single decaying cosmic string loop could unleash a pulse of energy equivalent to a staggering bomb, injecting a searing local hotspot into the otherwise smoothly cooling plasma exactly when the first nuclei were struggling to survive. And this is where the chemical history of the universe might have shifted. The standard model of Big Bang nucleosynthesis assumes a uniformly expanding, uniformly cooling cosmos. But a network of cosmic strings changes that picture into a stormy, clumpy, and intermittently reheated furnace. Imagine a vast, calm ocean cooling under a setting sun, and then a series of invisible fissures suddenly crack open, each one boiling a narrow channel of water back to a furious heat. Those channels would be the regions near decaying string segments, places where the local temperature momentarily spiked, the ambient photon density surged, and the delicate nuclear reactions we have described were thrown into chaotic overdrive. In these local hotspots, the deuterium bottleneck could have behaved very differently. Deuterium is, as we have stressed, remarkably fragile. A surge of high-energy photons from a nearby cosmic string cusp could have dissociated freshly forged deuterium back into lonely protons and neutrons, extending its bottleneck even in that pocket of space while the rest of the universe marched ahead. Conversely, the sudden injection of neutrons and protons from the decay could have fed a burst of fusion, cranking out a slightly altered ratio of helium-4 and lithium-7 in a clustered patch. Because the string network would be a global but irregular web dotted across the entire volume of the cosmos, no two regions would have received exactly the same disturbance. Some pockets would have been blasted by a nearby loop, others would have drifted untouched. The result is a chemically inhomogeneous universe where the primordial abundance of helium, deuterium, and lithium varied from place to place at a very fine-grained level. The lithium problem gains a fresh face in this scenario. If the cosmic string network was dense enough and the decay events frequent enough, the globally averaged lithium-7 abundance could have been driven down. How? Because in those searing local bursts, the same photodisintegration that shattered deuterium could also target lithium-7 nuclei, breaking them into lighter fragments. Meanwhile, in the cooler, undisturbed zones, lithium production proceeded normally, but those regions were not equally sampled when the first generation of stars formed. The earliest stars might have preferentially ignited in the slightly denser pockets seeded by the string decays, pockets that also happened to be lithium-poor because of the local heating. The ancient halo stars we observe today, those cosmic fossils we keep returning to, could be tracing only those chemically altered zones, giving us a skewed view of what the universe actually produced. This also leaves a distinct calling card, a pattern of scatter. If nucleosynthesis was perfectly smooth, every ancient star should show an almost identical lithium plateau, a flat line when you plot lithium abundance against stellar mass or metallicity. But if cosmic strings stirred the pot, we would expect a measurable variance, a genuine cosmic scatter in the lithium measurements from different old stars scattered across the Milky Way. Some current astronomical surveys are already hinting at a slightly larger dispersion in lithium abundances than pure noise would suggest, though the data is not yet definitive. A clear detection of such a primordial scatter, one that cannot be explained by stellar processes like atmospheric mixing or destruction, would be a seismic event. It would point directly away from a boring, featureless Big Bang and toward a turbulent beginning riddled with dancing fissures of spacetime. The cosmic string idea connects the very small to the very large in a way few other theories can. The same network of strings that tampered with the first atoms would have left other signatures written across the sky. Their gravitational wave roaring would still be echoing through the universe today, a faint but detectable background hum that experiments like the North American Nanohertz Observatory for Gravitational Waves, called NanoGrav, and its international partners are actively hunting using pulsar timing arrays. Evidence of a gravitational wave background consistent with a cosmic string network has already been tentatively reported, sending ripples of excitement through the cosmological community. Furthermore, the exact properties of the string network, its tension, its loop density, its decay rate, depend on the energy scale of the phase transition that birthed them. For strings formed at the electroweak scale, the energy injections into the primordial plasma would be modest, enough to tweak the light elements but not to shatter the entire paradigm. For strings born at the far more violent grand unification scale, the energy dump would be so cataclysmic that the entire observable universe would have been sterilized. The fact that we exist, that we see helium and deuterium so close to their smooth predictions and lithium only mildly depressed, already places an upper bound on how violent the cosmic string network could have been. This makes nucleosynthesis a remarkable probe of physics at energies trillions of times higher than any particle collider can reach. By studying the chemical abundances in a dozen ancient stars, we are effectively placing seismometers on the very fabric of reality, listening for the crack of space-time defects that snapped when the cosmos was younger than a heartbeat. The search is ongoing. Every newly discovered halo star with a pristine chemical surface adds another data point to the lithium scatter plot. Every year of pulsar timing data sharpens the hunt for the gravitational wave background. And every refinement of the nuclear reaction rates in our computer simulations tightens the predictions. The cosmic string theory of the first light elements reminds us that the night sky is not silent and still, but the cooling ember of a cataclysm in which even space itself might have stretched, groaned, and splintered under the strain of its own birth. If space itself could fracture into cosmic strings, then perhaps the very laws governing its stretch were once more fluid than we dare to dream. The solid bedrock beneath our feet is a lie we tell ourselves. General relativity, the elegant geometric theory that Einstein gifted the world more than a century ago, has passed every laboratory test and every celestial observation ever thrown at it. But the primordial kitchen of the Big Bang tested gravity at energy densities far beyond anything we can recreate. It is the one laboratory that can ask whether the strength of gravity itself was feeling its way into focus during those opening minutes. Alternative theories of gravity are not fringe fantasies. They are serious mathematical extensions that seek to heal cracks in our cosmic understanding. Cracks like the unknown nature of dark energy or the stubborn refusal of quantum mechanics to mesh with the bending of spacetime. Two families of these altered gravity models stand out as having direct and explosive consequences for the story of the first light elements. The first are scalar tensor theories, where the Newtonian gravitational constant is not actually constant at all. It becomes a dynamic field that shifts gently with cosmic time. The second are F of R gravity models, where the smooth curvature term in Einstein's equations gets replaced with a more complex function, letting the stretch of space accelerate or decelerate in subtle new ways. Both rewritings share a common thread. They can change the tempo of cosmic expansion in the very earliest epochs, precisely when the first atoms were battling for survival. The beat of that expansion defines everything. The Hubble parameter is the cosmic metronome, measuring how fast the universe swells at any given instant. In the standard picture, the first 3 minutes were a feverish deceleration, the cosmic clock racing from an inferno to a cool simmer on a razor-sharp schedule. If a modified theory of gravity made the expansion just a whisker faster, then the universe would have cooled more quickly during the vital moment when neutrinos decoupled. That frees out, as we have seen, locked in the neutron-to-proton ratio. A faster cooling leaves fewer neutrons, which trims the amount of helium forged later. A slightly slower expansion keeps the universe hotter for longer, preserving more neutrons and bloating the helium abundance beyond what ancient gas clouds reveal. The margin for error is breathtakingly slim. A deviation of even a few percent in the Hubble rate during nucleosynthesis would shift the helium-4 mass fraction by a full percentage point, an outsized change that telescopes would instantly detect. This makes the chemical fossil record a merciless auditor of gravitational heresy. Scalar tensor theories bring this to life with quiet elegance. In the most famous of them, the Brans-Dicke theory, a new scalar field ripples through the cosmos, and the effective strength of gravity weakens very slowly as the universe ages. When you wind the clock back to the first minutes, the gravitational pull was ever so slightly different, and the cosmic clock ticked to a subtly altered rhythm. The deuterium bottleneck, that fragile moment when nuclear construction could finally begin, is exquisitely sensitive to the expansion tempo. If the universe was stretching differently, the temperature at which deuterium survived destruction would drift, and the final census of deuterium compared to helium would carry the unmistakable fingerprint of a modified gravity. This is not just armchair philosophy. Researchers have computed precise predictions for these alternative scenarios and compared them against the measured abundances from pristine intergalactic clouds and the cosmic microwave background. The results cage the theories into extraordinarily narrow corners. Any scalar tensor model that drastically changed the expansion rate during nucleosynthesis would overshoot the deuterium and helium bounds so violently that the model would be ruled out. What remains allowed is a tiny, almost imperceptible window where the scalar field must have been almost completely frozen by the time the universe was 3 minutes old. In other words, even if gravity has an evolving face, it had to have put on its modern mask astonishingly quickly. The F of our gravity models face an identical crucible. They were developed largely to explain the modern acceleration of the universe without invoking dark energy, by tinkering with the very definition of space-time curvature. But that same tinkering, if it was active during the epoch of element formation, would have warped the Hubble rate. The expansion could have rippled and shuddered in ways that no longer smoothly follow the simple recipe of radiation-dominated slowing. The outcome is the same: too much extra acceleration and the helium abundance swells, too much deceleration and too little helium is made, while deuterium piles up in a way that clashes with the exquisitely accurate measurements from distant quasars. The lithium problem adds a further twist because any shift in the expansion rate that tries to tame the lithium-7 overabundance by altering the temperature of the reacting plasma simultaneously drags helium and deuterium out of their happy alignment. It is a multi-dimensional trap that few modified gravity theories escape without being squeezed into a tightly defined regime of parameters. But the fact that they do escape, even if only barely, is a triumph of scientific tenacity. It shows that our understanding of gravity is not a dead dogma but a living inquiry, constantly tested and refined against the oldest light in the sky. This transforms Big Bang nucleosynthesis into the most ancient and most powerful gravimeter ever conceived. Long before we could build detectors to listen for gravitational waves or send probes to measure the Shapiro delay of radio signals near the Sun, the nuclei of hydrogen, helium, and lithium were already voting on the correct theory of gravity. Every improved measurement of helium in a metal-poor dwarf galaxy, every new determination of deuterium in the shadow of a distant quasar tightens the screws on alternative models. It is a feedback loop across billions of years, where the atoms forged in the first 3 minutes and scattered into the voids now speak back to us about the very fabric of spacetime. The search continues because the lithium shortfall still nags, a splinter in the foot of the standard model. Could a sophisticated hybrid, a gravity theory that also interacts with a hidden dark sector, solve the lithium puzzle while keeping helium and deuterium pristine? That is an open frontier, a beckoning synthesis that might one day force us to rewrite the opening chapters of cosmic history yet again. And what makes this so electric is not just the answers we might find, but the profound realization that the rules of the game might have been carved not in the first second, but slowly, as the whole newborn universe itself expanded, cooled, and hardened into the elegant laws we mistake for eternal. A silent architect may have shaped the first atoms without ever touching them directly. Before the first stars flickered on, before galaxies spun into existence, the infant universe might have been threaded with colossal magnetic fields, invisible scaffolds stretching across the entire cosmos. These were not the gentle magnetic whispers that guide a compass needle. They were vast, coherent lines of force, perhaps born in the same shuddering instance that froze the fundamental forces apart or even smuggled out of the wild stretching of inflation itself. If such primordial magnetism saturated the early plasma, It would have acted as a hidden hand, gripping the charged particles that built the first elements and subtly steering the entire course of nucleosynthesis. The origin story of these fields is woven into the most violent phase transitions imaginable. During the electroweak era, when the electromagnetic and weak nuclear forces peeled apart like a splitting seam, the universe was a turbulent sea of charged currents. Swirling eddies of plasma could have spontaneously generated magnetic fields through a cosmic dynamo, amplifying tiny quantum fluctuations into gargantuan, galaxy-spanning webs. Inflation, that blinding burst of exponential expansion, could also have stretched microscopic field seeds to cosmic scales, imprinting the newborn universe with a faint but uniform magnetic hum. By the time the universe was 3 minutes old and cooking its first atomic nuclei, these fields may have already been strong and pervasive, not just a background hum but an active participant in the nuclear drama. The most immediate way such a field would make its presence known is through its energy. A magnetic field is not simply a direction in space. It stores tension and pressure, just like a stretched rubber band or a compressed spring. In the dense, radiation-soaked plasma of the early cosmos, this magnetic energy would add to the total density that drives cosmic expansion. A strong enough field would behave almost like a new kind of stiff fluid, resisting the normal rhythm of cooling and stretching. This extra energy nudges the Hubble parameter. The cosmic metronome we have seen is so exquisitely sensitive to beat a little faster. And as we know, any change in the expansion tempo during the deuterium bottleneck shifts the moment when nuclei can finally hold together, altering the final balance of helium, deuterium, and lithium. So even before the field directly touches a single proton, its sheer gravitational presence through energy density reshapes the entire kitchen temperature and all. But the magnetic field does not stop at bulk gravity. It speaks directly to the individual dancers in the plasma, because the early universe was a fully ionized soup, a roiling sea of electrically charged protons, electrons, and light nuclei. A charged particle cannot cross a strong magnetic field without veering. Its path gets bent into a tight spiral, like a car endlessly circling a roundabout. This trapping effect changes the effective reaction rates. For two protons to fuse, they must approach one another closely enough for the strong nuclear force to overpower their electromagnetic repulsion. In a calm, field-free plasma, this is a thermal game of chance. But in a magnetized soup, the particles waste energy circling field lines, which can either enhance collision rates by keeping them localized or suppress certain reactions by altering the quantum tunneling probability near Coulomb barriers. The net effect is deeply subtle and depends sensitively on the field strength and structure. The most fragile link in the chain, as always, is lithium-7. The pathway that leads to beryllium-7 and its eventual decay into lithium is a narrow road lined with charged particle reactions. A pervasive magnetic field could slow down or accelerate those specific steps, trimming the lithium yield without laying a finger on helium-4, which, once made, is extraordinarily difficult to shatter by magnetic means. Furthermore, magnetic pressure would introduce a new kind of spatial clumpiness. Field lines tend to bunch and tangle, creating pockets of higher and lower magnetic energy. The plasma trapped along dense field bundles would experience a different local expansion and cooling history than plasma drifting through magnetic voids. This creates exactly the kind of chemical inhomogeneity we explored with cosmic strings, a patchwork where some regions burned lithium more efficiently than others. The ancient halo stars we observe today might simply be sampling the magnetically altered patches, giving us a skewed, depressed average of the true primordial lithium abundance. The challenge, as with all these exotic solutions, is threading the needle between the three light elements. Helium-4, with its robust stability and massive abundance, is a stern judge. The magnetic energy density must be high enough to tweak reaction rates, but not so high that it bloats the expansion rate and inflates helium beyond the tight agreement with pristine gas clouds. Similarly, deuterium, the sensitive bottleneck survivor, cannot be pushed too far from its measured value. Researchers have run meticulous simulations that couple magnetic hydrodynamics to nuclear reaction networks, and they find a narrow window where a field of just the right strength, perhaps a few times 10 to the power of 16 Gauss in the plasma, can massage the lithium problem while keeping helium and deuterium almost untouched. That field strength, while immense by earthly standards, is consistent with what some models of inflationary magnetogenesis predict. Even more compelling, we may be seeing the ghostly remnants of these primordial fields today. Astronomers have detected faint magnetic fields threading the voids between galaxies, places so empty that no stellar dynamo or supernova should have seeded them. These intergalactic fossils point backward to a magnetic genesis before the first stars. Their measured strength, when wound back to the dense early universe, aligns tantalizingly with the window required to influence nucleosynthesis. It is not yet proof, but a whispering coincidence that invites deeper investigation. Telescopes like the Square Kilometre Array, now taking shape across continents, will map these cosmic magnetic webs with unprecedented precision, tracing their shape and strength across billions of light years. Every new measurement is a time capsule from the very minutes we are probing. The primordial magnetic field theory thus transforms the first light elements from a simple chemistry problem into a three-dimensional tapestry where gravity, particle physics, and electromagnetism all converge. It reminds us that the early universe was not a sterile vacuum but a turbulent, magnetized storm, and that the atoms in our bodies may have been forged not in calm silence but in the grip of invisible forces roaring across the newborn cosmos. As we continue our journey through the remaining theories, hold onto this image of a universe wrapped in magnetic scaffolding, because fields once thought to be passive decorations may soon be recognized as some of the most active sculptors of the first atomic dawn. The three-dimensional space we call home may be just a flimsy sheet drifting through a deeper invisible ocean. For decades, physicists have played with the staggering possibility that reality contains more dimensions than the familiar length, width, height, and time. In these bold constructions, our entire observable universe is a four-dimensional membrane, shortened to brain, afloat in a higher dimensional expanse known as the bulk. The bulk is not a void. It is a vast canvas where other brains may drift, where gravity seeps away, and where the true laws of physics unfold in all their native glory. During the blistering first 3 minutes of creation, this hidden architecture would not have sat idle. It would have reshaped the very rhythm of cosmic expansion, tweaked the strength of gravity, and left a subtle multi-dimensional signature stitched into the nuclei of the first light elements. Picture a thin slice of apple suspended in a dark gelatin dessert. The apple skin is our brain, containing every galaxy, every star, every particle of the standard model. The gelatin is the bulk, an unseen expanse of extra space. In such a setup, the forces of electromagnetism and the nuclear bindings are trapped strictly on the brain. They cannot leak into the extra dimensions, but gravity is different. Gravity is the geometry of spacetime itself, and it is free to roam through the entire bulk. That simple freedom changes everything. The apparent weakness of gravity in our three-dimensional world, why a tiny magnet can lift a paperclip against the pull of an entire planet, suddenly finds an elegant explanation. Gravity is not weak at all. It is merely diluted, its genuine ferocity spread thinly across all the dimensions we cannot see. During the epoch of Big Bang nucleosynthesis, this dilution effect would have dialed the effective gravitational constant to a different value than the one we measure today in our cold, settled cosmos. In the cramped heat of the early universe, the brain was very different. Extra dimensions might have been physically smaller then, compactified in a tight curl that allowed gravity to feel their presence more forcefully. Or perhaps the brain itself was roiled with tensions that changed how gravity coupled to matter on short timescales. The upshot is a universe where the cosmic metronome, the Hubble expansion rate, beat to a rhythm dictated by a hidden gravitational conductor. A slightly stronger effective gravity would have accelerated the expansion just a touch. A slightly weaker gravity would have let the universe linger in its hot state for a fraction longer. Either way, the freeze-out of neutrons and the shattering of deuterium would not have happened precisely as the standard textbook prescribes. This becomes a tangible, testable knob. In some brain models, the energy density of the early universe was not made solely of familiar radiation and matter. The warping of the extra dimension could have generated a new energy component, often called a radiant field, which behaves like a fluid that accelerates or decelerates the brain's expansion. In the earliest minutes, when the cosmos condensed from a searing quark soup into delicate nuclei, that extra energy pulse could have tilted the neutron-to-proton ratio. A faster expansion means an earlier decoupling of neutrinos, locking in a slightly higher neutron fraction and thus cooking more helium-4. A slower expansion would starve the universe of neutrons, leaving less helium but a richer leftover of deuterium. As we have seen, the observations of pristine gas clouds are merciless. The helium-4 mass fraction fits the standard model to within fractions of a percent. So the brain's extra dimension cannot run wild. It must be tightly corseted, compactified in a way that barely nudges the cosmic clock during those 3 minutes. The lithium problem adds a fascinating twist to this multi-dimensional detective story. In certain brain world models, the effective gravitational constant does not just shift uniformly. It can undergo a brief, transient spike or a gentle roll right as nucleosynthesis peaks. Imagine the expansion rate flickering just as the fragile beryllium-7 nuclei were forming, the short-lived precursor that decays into lithium-7. A momentary change in gravity, either through a changing Planck mass or a sudden adjustment in the size of the hidden dimension, could have trimmed that particular reaction pathway without spoiling the rest. This is the surgical precision that makes theorists so eager. The lithium shortfall that has stubbornly dogged standard cosmology might be the faint echo of a gravitational law that was briefly not our own. And then there is the ultimate signature, one that we may not need a particle collider to find. If the first atoms were forged under the influence of extra dimensions, then the pattern of light elements is not merely a local chemistry accident. It is a shadow cast by the true shape of reality. Constraints from the deuterium abundance in distant absorbing clouds, from the helium-4 mass fraction in dwarf galaxies, and from the lithium plateau in ancient halo stars all squeeze the parameter space of these brain models. The size of the extra dimension, the tension of the brain, the coupling of the radiant field all become numbers that must fit inside a narrow box. In many cases, the box is now so tight that large extra dimensions are ruled out. The ones that survive are tiny, rolled up far smaller than an atomic nucleus, yet still able to write their presence into the elemental census. Even more tantalizing, some brain models predict exactly the kind of gentle boost in expansion that slightly lowers the lithium abundance while keeping helium and deuterium untouched. They hint at a universe where the hidden dimensions are not just a mathematical curiosity, but a silent partner in the creation of every atom in your body. We can never stand outside the brain and see the bulk directly, but the Big Bang acted as a kind of particle accelerator powered by gravity itself. It compressed all of physics into a single, blazing instant, and the elements that survived are the fossilized data from that experiment. Every spectral measurement of an ancient star is a probe of the extra-dimensional geometry that may lurk just a millimeter beyond our senses. The search for primordial gravitational waves with instruments like the Laser Interferometer Space Antenna and next-generation cosmic microwave background arrays adds a complementary angle. A brain-world birth would have sent ripples not just through our three-dimensional space but through the bulk, producing a unique gravitational wave pattern that future observatories might catch. For now, the first light elements remain the most ancient and precise gauges we have. They whisper that the universe might be thicker than we know, and that the deepest secrets of creation are stitched not in exotic particles but in the very scaffold of spacetime itself, stretched across dimensions we are only beginning to imagine. The hidden dimensions were not the only seam that cracked as the cosmos cooled. Deep inside the first handful of microseconds, the entire universe underwent a meltdown in reverse, a shuddering transformation so profound that it changed the very meaning of what particles could exist. This was the quark-hadron phase transition, the forgotten pivot point that may have silently sculpted the raw materials for every atom that followed. To grasp it, we must strip matter down to its absolute essence. Protons and neutrons are not fundamental. They are composite bundles, tight little bags of more primitive ingredients called quarks, stitched together by particles called gluons, the carriers of the strong nuclear force. Today, quarks are caged so tightly inside protons and neutrons that they can never be pried free. But in the first fleeting moments after the Big Bang, the temperature soared so high that even the glue of the strong force melted. The entire cosmos became a perfect ocean of free quarks and gluons, a state physicists call the quark-gluon plasma. It was a seething, almost frictionless liquid, not of atoms or nuclei, but of the alphabet of reality itself, loose and untethered. Then came the crash. The universe had been expanding and cooling at a ferocious pace. When the age of the cosmos ticked to roughly 10 microseconds, the temperature plunged past a critical threshold of about 2 trillion degrees Kelvin. The strong force, which weakens at short distances in a bizarre quirk of quantum physics, abruptly regained its grip. The previously free quarks slammed together in groups of 3, locking instantly into the protons and neutrons that would become the building blocks of everything. This was not a gentle dimming of a light bulb. In many theoretical frameworks, it was a violent phase transition, a metamorphosis of the vacuum itself. Imagine a vast stadium filled with a cheering crowd of individual people, all moving chaotically in every direction. Then, in a single instant, a signal rings out and the crowd locks arms, snapping into rigid trios that can no longer break apart. The stadium transforms from a fluid sea into a solid grid of linked clusters. That is the switch from a quark-gluon plasma to a gas of hadrons. The details of this transition are everything. Cosmologists debate whether it was a sharp first-order transition or a smooth crossover. A first-order transition is a true cosmic freeze, like water crystallizing into ice. It releases latent heat, nucleates bubbles of the new hadron phase inside the old quark sea, and generates violent density shocks as the bubbles expand and collide. In that tempest, the transport of baryons, the heavy protons and neutrons themselves, would not have been a gentle drift. The expanding bubble walls could act like cosmic snowplows, sweeping up quarks and preferentially pushing certain species ahead. Because neutrons and protons carry slightly different masses and interact with the bubble wall with different efficiencies, the advancing phase boundary could sift the quark soup, creating pockets rich in protons and others rich in neutrons. This is the microscopic birth of the clumpy universe we touched upon earlier, not from density waves after the fact, but from a deep chemical segregation driven by the very act of particle creation. A crossover transition, on the other hand, is a seamless blur. It is less a sharp freeze and more a gradual thickening, like honey slowly stiffening in a cooling jar. Yet even a smooth crossover is not powerless. Near the transition point, the strong force becomes nearly scale invariant, and fluctuations in the energy density of the plasma can be amplified to enormous sizes. These critical fluctuations could leave behind a faint, wispy geography of hot and cold spots, each with its own slightly different local recipe of neutrons to protons. The baryon transport in a crossover is subtler, a diffusion-driven drift rather than a snowplow, but it still imprints a hidden patchiness on the baby universe. Why does this fleeting moment, lasting barely a few microseconds, hold such sway over the first light elements that formed minutes later? Because it set the initial condition for every nuclear furnace that followed. The neutron-to-proton ratio was not cleanly dictated by neutrino freeze-out alone. It was also preloaded by the output of the quark-hadron transition. If the transition was violently first-order, the neutron-rich bubbles that splashed into existence would have been the very same neutron pockets that later burned lithium with unusual ferocity or left helium slightly boosted in clumps. If the transition was a crossover with critical fluctuations, those early wiggles in density and composition provided the seeds for the chemical scatter we still hunt in ancient halo stars. The quark-hadron transition, therefore, acts as the first great sculptor in the cosmic chain, the moment when the formless ocean of pure color charge resolved into the sturdy bricks of ordinary matter. Experimental physics has reached back to touch this very event. Giant colliders like the relativistic heavy ion collider in New York and the Large Hadron Collider in Switzerland slam heavy atomic nuclei together at blinding speeds to create miniature droplets of quark-gluon plasma. These fleeting fireballs, smaller than an atomic nucleus and lasting less than a trillionth of a second, cool and recombine just as the early cosmos did. The data from these experiments reveal that the transition is remarkably smooth, a crossover rather than a sharp first-order jump, at least near the vanishing chemical potential that mirrors the early universe. If that is correct, then the Baroque scenarios of snow-plowing bubble walls and violent neutron segregation become less likely. But the experiments also show that the plasma is a near-perfect liquid with astonishing collective flows, meaning that even in a crossover, the transport of baryons could be subtly sculpted by lingering pressure gradients that affect protons and neutrons slightly differently. The search for the gravitational wave echo of a first-order transition continues as well. A violent bubbling transition would have rung space-time like a struck bell, and the resulting gravitational waves, though stretched to nanohertz frequencies today, would be detectable by pulsar timing arrays. The fact that pulsar astronomers are now seeing hints of a low-frequency hum could, in principle, be the genuine sound of quarks locking together into the first protons. That would be a direct detection of the cosmic phase transition, a confirmation that our chemical origins were not a placid thaw but a roaring, turbulent birth. And this brings us back to the same stubborn lithium problem that shadows every theory. If the quark-hadron transition birthed even a mild inhomogeneity, a faint patchwork of slightly different neutron fractions, then the lithium we measure in metal-poor stars today might be a biased sampling of those original pockets. The standard model of nucleosynthesis assumes a perfectly mixed, uniform starting point. That assumption is a philosophical choice, not an established fact. Every glitch in the transition, every bubble wall that swept aside a few extra neutrons, writes a small correction into the final elemental tally. The combined constraints from helium-4, deuterium, and the cosmic microwave background still hem these corrections into a tight box, but the box is not empty. A window remains for a transition that was neither a violent explosion nor a perfectly featureless blur, but something in between, a turbulent smoothing that left the finest possible fingerprints on the light that later shone from the first stars. As we move deeper into the theories that re-examine the nuclear reaction rates themselves, keep this picture of the quark-hadron transition at the front of your mind. It stands as the deep floor of the cosmic kitchen, the moment when the very substances that would later cook into elements first snapped into existence, and it whispers that the seeds of the lithium anomaly might have been planted not in the cooking, but in the preheating of the universe itself. The quark-gluon plasma was never just a calm ocean of simple matter. It was a churning cauldron where the most exotic form of substance ever imagined might have briefly flickered into existence. Strange quark matter is not just a hypothetical curiosity. It is a genuine prediction of nuclear physics, a proposed new ground state of the strong nuclear force, denser and more stable than the ordinary protons and neutrons that built our world. The hypothesis is both terrifying and beautiful. What if the protons and neutrons we have always assumed are the ultimate stable bricks of reality are actually just a metastable illusion, a temporary phase, while the true lowest energy state of matter is made of something far stranger? In the searing heat of the quark hadron transition 10 microseconds after the Big Bang, the entire universe was drenched in a soup of free quarks. The familiar up and down quarks, the lightweights that build protons and neutrons, were not alone. A heavier, more elusive third species also swirled in that primordial fire. This was the strange quark, a particle normally locked away inside fleeting particles produced in high-energy collisions. In the crushing density of the early cosmos, the strange quark could have teamed up with its lighter cousins in equal measure. The result would have been tiny, ultra-dense droplets where up, down, and strange quarks clustered together in roughly equal numbers. These droplets are called strangelets, and if they truly formed during that fierce transition, they could have acted as a hidden sink, a cosmic trapdoor that swallowed a fraction of the universe's ordinary material before the first atoms ever had a chance to cook. The physics behind this idea traces back to a radical proposal made by physicist Edward Witten in 1984. Strange quark matter, he argued, might be more stable than iron, the most tightly bound ordinary nucleus. If that is true, then every atomic nucleus in our bodies, every proton and neutron in every star, is merely waiting, prevented from collapsing into a strangelet only by a towering energy barrier that has never been overcome. The early universe, however, had no such barrier. At temperatures of trillions of degrees, the soup could sample every possible configuration, including the strange one. As the cosmos cooled through that fierce microsecond window, some pockets of the plasma, perhaps seeded by the density fluctuations we discussed, could have condensed directly into droplets of strange quark matter instead of snapping into ordinary protons and neutrons. These strangelets would be fundamentally different from any nucleus. They would not be composed of protons and neutrons glued together by the residual strong force. They would be a single, coherent bag of quarks with a density surpassing even that of a neutron star. A strangelet the size of a dust mote could outweigh an aircraft carrier. And once formed, it would be nearly impossible to destroy, an indestructible relic of the earliest instant of matter itself. The connection to our story of the first light elements cuts to the very heart of the lithium problem. Ordinary Big Bang nucleosynthesis is a census that counts every proton and every neutron. The baryon density, measured exquisitely from the cosmic microwave background, tells us exactly how many baryons existed per unit volume when the proverbial cooking began. The entire standard recipe relies on the assumption that every one of those baryons participated fully in the nuclear dance, either as a free proton or neutron available for fusion. But what if some of them were already gone, locked away inside strangelets before the universe was even 3 minutes old? Strangelets would act as neutron sponges, but far more utterly than any ordinary nucleus. If a free neutron struck the surface of a strangelet, it would not bounce off or trigger a conventional reaction. It would be absorbed, its individual identity erased. The strangelet would grow by one additional baryon, but that neutron would vanish from the light element ledger. It would contribute nothing to the eventual helium, deuterium, or lithium census we measure today. This is the key mechanism. By hiding a fraction of the available neutrons inside indestructible, dense nuggets of strange matter, the universe would have taken its foot off the gas pedal of standard nucleosynthesis. Fewer neutrons means less helium-4 is forged overall. It means the deuterium bottleneck plays out in a neutron-poorer environment. and crucially, it means the fragile chain that overproduces lithium-7 is starved of the raw material it needs. The magnitude of the effect could be finely tuned. If strangelet formation absorbed just a few % of the free neutrons, the lithium-7 prediction would shift downward significantly, edging toward the observed value in ancient halo stars. At the same time, helium-4, with its robust abundance, would ease only slightly lower, potentially aligning even more sweetly with the lower end of astronomical measurements. Deuterium, which is highly sensitive to the available baryon density, would feel the shift too, but because the total baryon count inferred from the microwave background remains unchanged, the subtle rearrangement of baryons between ordinary particles and hidden strange matter could produce a new chemical fingerprint that matches all three light elements more harmoniously than the standard model. The strangelet hypothesis gains traction from an entirely different direction: the ongoing search for stable strange matter in the modern cosmos. If strangelets were forged in the Big Bang, a portion should have survived to this day, drifting through the galaxy as a component of dark matter. They would be far denser than any known substance, yet chemically inert, because they would carry an enormous positive electric charge in their core, repelling ordinary matter so fiercely that they could pass through a planet without a single nuclear interaction. Experiments have tried to detect these relics in several ingenious ways. Seismic detectors have hunted for the unique ringing signature a strangelet would leave if it zipped through the solid Earth, a needle-thin column of shock heating slicing through rock. Satellite-borne magnetic spectrometers, like the Alpha Magnetic Spectrometer on the International Space Station, have searched for the bizarrely high mass-to-charge ratio that a strangelet would display when caught in a detector. So far, the searches have come up empty, placing ever tighter limits on the concentration of strangelets in our galactic neighborhood. But a small abundance, precisely the kind that could tweak nucleosynthesis without overclosing the modern universe, remains well within the allowed window. Another tantalizing clue comes from extremely compact stellar objects. Neutron stars are already stupendously dense, but some researchers suspect that a particularly massive or rapidly spinning neutron star might convert into a strange star, an entire stellar remnant made of strange quark matter. By measuring the masses and radii of neutron stars through X-ray observations and gravitational wave events, astronomers can check whether the equation of state, the relationship between pressure and density, matches the predictions of strange matter. The results so far are ambiguous, but the existence of several neutron stars with masses above 2 solar masses puts strain on some strange star models, while leaving others entirely viable. The formation of strangelets during the quark-hadron transition is not a guaranteed event. It depends exquisitely on details we still cannot compute with certainty, such as the surface tension between ordinary nuclear matter and strange quark matter, and the exact violence of the transition itself. If the transition was a smooth crossover with no sharp phase boundaries, the opportunity to nucleate droplets of strange matter might have been lost entirely. But if it was even briefly a first-order transition with bubbling phase separation, then strangelet formation becomes a plausible, perhaps even inevitable, outcome. This places the strange quark matter hypothesis at the intersection of collider physics, astrophysics, and cosmology. The same experiments that recreate miniature drops of quark-gluon plasma at the Large Hadron Collider and the relativistic heavy ion collider are also probing the equation of state that determines whether strangelets can condense. Every measurement of how the plasma flows, how it scatters, how it hadronizes, feeds back into our understanding of what might have condensed in that ancient universal moment. The picture that emerges is one of a cosmos far richer and more chemically complex in its opening act than we once believed. The standard model of nucleosynthesis is a triumph, but it may be a triumph that overlooks hidden vaults of matter. The lithium problem refuses to fade because it may be the faint voice of these vanished neutrons, absorbed into dark, dense ghosts that still drift unseen through the void. It pushes us to consider that the stable matter of our daily lives is not the full story, and that the ground state of the strong force might hold secrets we are only beginning to decode. Every ancient star we measure, every blank patch of sky scanned for strangelets, every collider run that maps the quark-gluon plasma, is a chapter in the unfolding saga of whether the universe's first atoms were truly alone, or whether they shared their fiery nursery with indestructible droplets of a reality far stranger than our own. A wholly different hidden particle may have quietly tamed the primordial heat rather than stealing neutrons from the ledger. Axions are among the most feather-light dark matter candidates ever conceived, so staggeringly light that their mass may be 10 trillion times smaller than an electron. Yet they could have flooded the early cosmos in such staggering numbers that their collective ghostly presence would have acted like a soft, invisible refrigerator, gently dialing down the temperature of the particle broth exactly when the first nuclei were taking shape. This is the axion cooling effect, and it turns the search for dark matter into a delicate thermometer reading the oldest heat in the universe. Axions were originally invented to scrub away a puzzling imperfection in the strong nuclear force, a parameter that ought to show time asymmetry but somehow does not. Physicists realized that a new field permeating all space could naturally cancel this anomaly, and the ripple in that field would manifest as a particle, the axion. Independent of that origin, theorists soon recognized that axions also possess the perfect hallmarks of dark matter. They would be produced in the early universe through non-thermal processes, filling space with a vast, cold ocean of ghostly particles that barely interact with ordinary matter. The neat twist is that even the feeblest coupling to light, just a whisper of a connection, would have been enough to reshape the thermal history of the cosmos. In the rolling boil of the Big Bang's first few minutes, photons, particles of light, dominated the energy budget. If axions possess an ultra-faint coupling to photons, then the searing plasma could have converted some of those photons directly into axions. This process, known as the Primakov effect, would have been active while the universe was dense and hot. The newborn axions, once produced, would slip away from the hot broth almost instantly, carrying an unseen cargo of thermal energy with them into the void. They would not bounce, scatter, or linger. They would simply drain away like slow evaporation from a steaming pot. Crucially, the neutrinos had already decoupled from the plasma a full second after the Big Bang and would not feel this late energy drain. The photon bath would thus be selectively cooled relative to the neutrino background. That subtle nudge in the thermal balance writes itself directly into the cosmic expansion metronome. A cooler photon bath means that the total radiation energy density during nucleosynthesis is slightly lower than the standard model assumes. Recall that the expansion rate of the infant cosmos depends exquisitely on how much radiation is packed into each cubic centimeter. With photons a little cooler, the universe unbuckled a tiny bit slower, and as we have seen throughout our journey, a slower expansion shifts the whole choreography of element building. The weak interactions that interconvert protons and neutrons freeze out at a slightly different temperature, leaving a marginally lower neutron fraction. Fewer neutrons, in turn, means less helium-4 is forged from the primordial bellows, and the abundances of deuterium and lithium shift in lockstep. That is the elegant magic of the axion cooling scenario. The stubborn lithium-7 shortfall is joined by a lesser-known but equally nagging tension: the fact that some of the most precise measurements of primordial helium in pristine gas clouds actually suggest an abundance a hair lower than the central theoretical prediction. Standard Big Bang nucleosynthesis, with its 3 neutrino species, produces a helium-4 mass fraction just above 24.7%. But certain deep observations of metal-poor dwarf galaxies point toward a value a fraction of a percent lower, right around 24.5%. The axion cooling effect can gently massage the helium prediction downward, driving a better match to those lower measured values while simultaneously tugging lithium-7 in the right direction. It is not a brute force fix, but a subtle tuning that harmonizes the entire elemental orchestra with a single new stroke of the baton. The testability of this idea is what makes it so compelling. The strength of the action-photon coupling is not a free, unbounded knob. It is sharply constrained by a web of astronomical and laboratory experiments. The same actions that cooled the early universe would have streamed out of the Sun's core today. Telescopes like the European Space Agency's X-ray multi-mirror mission, known as XMM Newton, have pointed at the Sun and searched for the soft X-ray glow that actions reconverted into photons should produce in the solar magnetic field. The absence of such a glow already tightens the coupling to an extremely narrow sliver. Even more powerfully, the cosmic microwave background itself keeps a rigorous account. A late energy drain from the photon bath would alter the pattern of hot and cold spots mapped by the Planck satellite, effectively changing the inferred number of relativistic species. The data currently allow for a tiny decrement, a hint that the photon bath might indeed be slightly cooler than expected relative to neutrinos. It is far from proof, but it is a crack in the door through which an action could slip. The action's dual nature makes it a unified field theory in miniature. The same particle that solves a deep puzzle in the strong nuclear force that composes the invisible dark matter scaffolding galaxies could also be the quiet sculptor that cooled the first fire just enough to leave the exact pattern of light elements we measure today. If a laboratory experiment, such as the action dark matter experiment probing for microwave signals in a resonant cavity, or the any light particle search peering down a shielded optical tube, detects the action, we gain not just a dark matter candidate but a new calibration lever for the cosmic oven. The primordial abundances of helium, deuterium, and lithium would suddenly transform into precision measurements of the action-photon coupling, turning the Big Bang into a benchmark for untested physics. This leaves us with a vivid picture of the first 3 minutes, not as a simple, smooth freeze, but as a delicate thermal ballet where every invisible player counted. Actions, if they existed in the right numbers with the right whisper of a connection to light, would have been the silent chill that kept the cosmic kitchen from overheating, a tiny breath of cold through an open door that shaped the very atoms of which you are made. A sudden surge of invisible energy may have shoved the cosmos faster than we ever expected. The universe we see today is coasting on the gentle push of dark energy, a mysterious force that is stretching space apart at an ever-increasing rate. Most cosmologists assume this dark energy was either completely dormant or utterly insignificant during the first few minutes of creation. But a bold and growing family of theories proposes exactly the opposite. What if a short-lived, ferocious burst of dark energy flickered to life just before or even during the forging of the first light elements, only to vanish almost as quickly as it appeared? This is the hypothesis of early dark energy, and it cracks open a window onto a universe where the cosmic clock itself was briefly and violently tampered with. To picture how early dark energy might have worked, think of a ball rolling across a vast, gently sloping landscape. That ball represents a scalar field, an invisible energy field that fills space, much like the one we met when discussing drifting fundamental constants or the action. In the modern universe, such a field would sit pinned at the bottom of its valley, perfectly still, contributing almost nothing to the cosmic budget. But in the blistering heat of the early cosmos, the landscape of physics was a wilder place. The field could have been perched far from its resting point, perhaps stuck on a high plateau. As the universe expanded and cooled, the field began to roll slowly toward the bottom of the valley. And while it rolled, it carried an enormous reservoir of stored energy, a kind of tension in the fabric of space that behaved very much like the dark energy we observe today, but squeezed into a far fiercer, more concentrated dose. This rolling field would have acted like a temporary inflating pump, adding a new, stiff component to the cosmic soup that forced space to stretch apart faster than ordinary radiation and matter alone would demand. The timing of this rolling episode is everything. For the idea to affect the first light elements without shattering the later history of the cosmos, the field must have surged into dominance and then gracefully faded away within a breathtakingly narrow window. Some models place the early dark energy spike right around the time of neutrino decoupling, roughly 1 second after the Big Bang. Others let it linger a little longer, injecting extra expansion energy into the crucial 3-minute nucleosynthesis window itself. The common thread is a changed heartbeat. The Hubble parameter, the cosmic metronome we have learned to watch so closely, would have been temporarily boosted. The universe, in simple terms, would have been running a fever. Its expansion briefly outpaced the standard model's expectations, cooling more rapidly for a short spurt. This faster cooling rate, even if it lasted only a handful of minutes, would have left a permanent chemical scar on the newborn atomic nuclei. The first target of that scar is the freeze out of the weak nuclear interactions that interconvert protons and neutrons. In the standard story, these reactions shut down at a precise temperature, locking in the neutron-to-proton ratio that seeds all later element building. Early dark energy speeds up the clock. The universe cools through that critical temperature band a little sooner, a little faster, because neutrons are slightly heavier and more sluggish to form in a cooling cosmos. A hastier freeze-out tends to leave behind a marginally smaller fraction of neutrons relative to protons. This is a subtle shift, but it cascades through every subsequent nuclear step. Fewer neutrons, as we have seen again and again, means less helium-4 is forged when the deuterium bottleneck finally breaks. The helium-4 abundance, that gold standard measurement from pristine gas clouds, drifts downward. In some versions of the theory, this gentle reduction actually brings the predicted helium mass fraction into more perfect alignment with the lower end of astronomical measurements, harmonizing a tension that had no easy fix. The deuterium bottleneck itself is equally vulnerable. Deuterium survival depends on the temperature dropping far enough that ambient photons can no longer shatter it. If early dark energy accelerated the cooling dash, the universe could have slipped through this danger zone more briskly. That might leave slightly more deuterium unburned, or it might tweak the precise temperature at which the bottleneck broke, shifting the final census of this fragile isotope in ways that astronomers can check against the absorption lines from distant quasars. The interplay is exquisitely delicate, a dance of competing effects that powerful computer simulations must untangle. But the core insight remains. A brief kick in the cosmic expansion writes itself directly into the elemental abundances, making nucleosynthesis a seismometer for a force that otherwise left no visible trace. Then we arrive again at the stubborn lithium problem. The standard model overproduces lithium-7 by a factor of 3 compared to the oldest stars. Early dark energy offers a new scalpel. By shifting the temperature history during the vital minutes when beryllium-7 was forming, the rolling scalar field can alter the production pathway for lithium. A faster cooling timeline can suppress the nuclear reactions that build beryllium-7, the parent nucleus that later decays into lithium-7, trimming the final lithium yield without over-punishing helium or deuterium. The effect can be precisely tailored by adjusting 2 key parameters: the amount of energy the field carried relative to the rest of the cosmic soup and the exact moment it faded from prominence. In the most elegant scenarios, the field was already nearly gone by the time nucleosynthesis peaked, but its lingering shadow on the expansion tempo was enough to erase just the right amount of lithium while leaving the other light elements almost unruffled. This surgical precision makes early dark energy a deeply attractive candidate for addressing the lithium anomaly without breaking the standard model's many other successes. The story does not end with chemistry. A burst of early dark energy would have also left a faint ghost in the cosmic microwave background, the oldest light we can see. The same accelerated expansion that tweaked the elemental abundances would have shifted the sound horizon, the distance that pressure waves could travel in the early plasma. This distance acts as a standard ruler imprinted on the pattern of hot and cold spots mapped by the Planck satellite. Too much early dark energy, and the ruler length shifts in ways that clash with Planck's exquisite measurements. This cross-check has already been used to put powerful upper limits on the strength and duration of any early dark energy episode. The data currently favor a very small injection of extra energy, if any, occurring within a narrow window around the epoch of matter radiation equality, slightly later than nucleosynthesis. But the constraints are not yet airtight. The latest analyses from the Atacama Cosmology Telescope and South Pole Telescope are probing finer angular scales, and some intriguing hints suggest that a modest dose of early dark energy could actually ease several other cosmic tensions, including the slightly different expansion rates measured in the local universe versus those inferred from the ancient microwave sky. This makes early dark energy a candidate that might unite the lithium problem with the broader puzzle of why the modern cosmos seems to be stretching a bit faster than expected. The rolling scalar field hypothesis transforms the first 3 minutes from a closed chapter into a dynamic probe of fundamental physics. It suggests that the dark energy we now see as a gentle, persistent hum was once a roaring, transient shout, and that the atoms in the oldest stars are the fossilized sound of that shout. Every measurement of helium in a blue compact dwarf galaxy, every spectrum of deuterium in a quasar shadow, and every lithium tally in a metal-poor halo star becomes a check on the energy content of the universe during its most formative minutes. The search for early dark energy is thus a search for the ghosts of forces that flared and died before the first star ever shone, leaving only the faintest chemical whispers in the light that reaches our telescopes after a voyage of more than 13 billion years. A ghost of gravity itself may have lingered long after the other particles had frozen into atoms. The gravitino is not merely another phantom in the particle zoo. It is the hypothetical supersymmetric twin of the graviton, the quantum carrier of the gravitational force. If nature truly obeys supersymmetry, then during the first blazing instance of the Big Bang, gravitinos would have been forged in staggering abundance, sown directly from the heat of the expanding cosmos. Most superpartners are brutally unstable, crumbling in a flash, but the gravitino, if it is the lightest member of the supersymmetric family, would be kept alive by an almost absurdly feeble connection to ordinary matter, a coupling throttled by the very weakness of gravity itself. That frailty turns it into a ticking clock. While the standard nuclear kitchen finished its work in 3 minutes, the gravitino could have drifted on for hours, days, or even centuries before its internal timer ran out. And when it finally decayed, it would not go quietly. Each vanishing gravitino would erupt into a searing spray of photons, electrons, and hadronic particles, a delayed detonation that slashed through the peacefully cooling gas of the early universe. That late injection is the scalpel that theorists turn toward the stubborn lithium problem. In the standard recipe, lithium-7 was overproduced by a factor of 3, a glaring mismatch with the oldest stars. But a gravitino decay delivers exactly the kind of post-nucleosynthesis photodisruption we have seen, can selectively prune fragile nuclei. High-energy photons from the decaying gravitino stream through the thinning fog and slam into lithium-7, cleaving it into lighter fragments like helium-4 and tritium. Because helium-4 is so tightly bound, it weathers this late barrage with remarkable stoicism, its abundance barely shifting. The net result is a cosmic edit. Lithium-7 is partially erased, its final tally pushed down toward the observed plateau, while the helium and deuterium predictions remain nearly untouched. It is a surgical strike, and the gravitino wields the blade, but surgical strikes require inhuman precision. The same photon shower that breaks lithium-7 can just as easily shatter deuterium, a nucleus almost as fragile. A single mistuned parameter, the gravitino's mass, its lifetime, or its decay branching ratios, and the delicate deuterium bottleneck we have so carefully preserved would come undone. The universe would be left with too little deuterium to match the measurements from distant primordial clouds. Even more treacherous is the possibility of overproducing helium-3. The hadronic spray from gravitino decay can trigger secondary fusion reactions, sowing stray protons and deuterium into helium-3, a rare light isotope that astronomers also monitor in pristine gas. If the gravitino dumped too much energy or decayed along the wrong channels, it would leave a helium-3 excess that stars do not show. The theory thus threads a needle eye. The gravitino mass must fall within a narrow band, likely near the tera-electronvolt scale, heavy enough to produce the hard photons that break lithium, but not so heavy that the hadronic cascade runs rampant. Its lifetime must be exquisitely poised, living past the standard nucleosynthesis window so as not to disrupt the freeze-out, yet decaying before the universe grew too thin for its particles to find any nuclei left to split. This fine-tuning is not a fatal flaw. It is a challenge that points to a deeper structure. In many supersymmetric models, the gravitino's properties are linked to the same hidden sector that gives rise to dark matter. The lithium problem, the helium-3 constraint, and the dark matter relic abundance all become coupled dials, and fitting them all simultaneously may reveal the precise architecture of supersymmetry breaking itself. Experimental constraints from the cosmic microwave background and from light element surveys already fence the gravitino's playground tightly, but a viable window still lingers. Future searches for a subtle gamma-ray glow from gravitino decays, or for the missing energy signature of superpartners at colliders, could corner the particle and test its chemical legacy directly. In this view, the lithium shortfall is not an embarrassment to cosmology, but a faint, precious stain left behind by the very force that holds the cosmos together, waiting to be decoded. A cosmic annihilation of unimaginable scale is the only reason you exist at all. The universe we see, every star, every planet, every living cell, is built entirely from matter. Yet the laws of physics, as we understand them, insist that the Big Bang should have forged matter and antimatter in perfect mirror image pairs, equal quantities of each, destined to meet and obliterate one another in a blaze of pure energy. The fact that a tiny sliver of matter survived to build the galaxies is the baryon asymmetry problem, one of the deepest unsolved mysteries in all of science. The standard story is that an ancient, subtle twist in the laws of particle physics tipped the scales in the very first instance, leaving a residue of matter after a universe-wide war of mutual destruction. But what if that war was not entirely over by the time the first atomic nuclei began to stitch together? What if isolated islands of antimatter, stubborn holdouts drifting through the expanding fire, managed to avoid the initial purge and only met their end minutes later, during the very era when light elements were being forged? This is the theory of surviving antimatter domains, and it recasts the gentle cooling of the standard cosmic kitchen into a battlefield lit by delayed, catastrophic flashes. Picture the infant universe not as a single smooth ocean, but as a turbulent foam riddled with pockets. In the accepted narrative, any antimatter pocket that touched a matter wall would have annihilated almost instantly, vanishing in a searing burst of high-energy gamma rays long before the cosmos was even 1 second old. But some physicists have proposed that exotic physics during the quark-hadron transition or even earlier could have sculpted the primordial soup into a froth of separated domains, some rich in matter, some rich in antimatter, kept apart by thin, stable walls of energy. These walls might have acted like fire breaks, preventing the two opposite substances from finding each other until the universe had stretched and cooled considerably. By the time those walls finally dissolved, likely triggered by a drop in temperature or a phase transition change, the universe was already deep into the minutes of nucleosynthesis. The ordinary light element cooking was well underway. Deuterium had broken through its bottleneck. Helium-4 was being assembled. The fragile chains leading to lithium were knitting together. And then, scattered across the cosmos, the surviving antimatter domains would have touched ordinary matter, and the subsequent annihilation would not have been a quiet fizzle. It would have been an intensely localized detonation of pure radiation, firing gamma rays and energetic particles into the surrounding gas. Those delayed gamma ray flashes are the heart of the theory. They would have acted as a kind of nuclear sandblaster, hitting freshly minted nuclei with enough energy to shatter them apart. The mechanism is the same photodisintegration we have encountered before, but the delivery is uniquely brutal and patchy. A wall of gamma photons erupting from a nearby antimatter domain would have streamed through the cooling plasma and struck the most fragile nuclei first. Deuterium, as we have seen again and again, is exquisitely easy to break. A relatively soft gamma photon can pry its single proton and neutron apart. Lithium-7 is the next in line, its nucleus sitting on a knife edge of stability. A harder photon can cleave lithium-7 into helium-4 and tritium, effectively erasing it from the record. Helium-4, by contrast, is a fortress. Its tight binding makes it stubbornly resistant to photodissociation, meaning it would sail through these annihilation bursts with barely a scratch. This selective vulnerability is the precise surgical profile that the lithium problem demands. The standard model overproduces lithium-7 by a factor of 3 and gets deuterium and helium beautifully right. If delayed antimatter annihilation swept through the cosmos after the main nucleosynthesis events had already set the helium and deuterium abundances, it could have trimmed the excess lithium-7 without spoiling those other matches. In this telling, the lithium shortfall is not a mistake in the cooking but a late scorching from a battle still raging in the background. The effects would not have been uniform. Because the antimatter domains were isolated pockets, the annihilation events would have been scattered like landmines across the newborn universe. Some regions got blasted and had their lithium pruned. Others sat in quiet stretches of space and preserved their full primordial lithium bounty. This naturally introduces a chemical patchiness, a cosmic variance that could explain why some ancient stars show slightly different lithium levels, a phenomenon astronomers have been painstakingly documenting for decades. The oldest metal-poor halo stars in our galaxy might not all sample a perfectly mixed, uniform primordial soup. They might instead echo the random geography of annihilating antimatter bubbles, with some stars born from gas that had been scoured clean of lithium and others born from pockets that saw little to no destruction. The average lithium abundance we measure today would then be a blend, a weighted sum over a landscape of chemically scarred and chemically pristine patches, with the scars winning out in the average tally. The challenge, as always, is the brutal precision of the cosmic accounting. Deuterium is only marginally more stable than lithium against photodisruption. A gamma ray burst energetic enough to chip away at lithium-7 can equally well begin chipping at deuterium if the photon spectrum is slightly too hard or the burst too dense. Even a modest dent in the deuterium abundance would throw the exquisite alignment with quasar absorption measurements out of step. The antimatter domains therefore need to be precisely calibrated. They must be massive enough with enough total antimatter content to drive a significant wave of photodestruction across a substantial fraction of the universe. Yet they must also produce photons with an energy spectrum that falls off just before reaching the deuterium dissociation threshold. This spectral sculpting is not impossible, but it requires a delicate balance between the temperature of the annihilation fireball, the density of the surrounding plasma, and the speed with which the energy degrades through Compton scattering against electrons. Theorists who model these scenarios find a narrow but genuine window where the lithium-7 drops by the required factor while deuterium and helium stay inside their observed bounds. This connects the lithium problem directly to the fundamental origin of matter's dominion over antimatter. The same deep physics that explains why you are made of protons and not annihilated into photons could also have set the timing, size, and distribution of those primordial antimatter pockets. In some unified theories, the separation of matter and antimatter occurred through a mechanism called spontaneous baryogenesis, or through the dynamics of a new scalar field that sorted regions like a cosmic mail sorter. The delay before annihilation would then be a natural consequence of the field relaxing, and the energy spectrum of the resulting gamma rays would be imprinted by the field's properties. This makes the light element abundances a probe of baryogenesis itself, a way to test theories of the universe's ultimate genesis that would otherwise be entirely inaccessible to laboratory experiments. The current limits from the cosmic microwave background and from gamma-ray sky surveys already constrain how many such domains could have existed and how late they could have annihilated, but the allowed parameter space still holds room for a solution to the lithium anomaly. The idea of antimatter domains surviving into the era of nucleosynthesis transforms the early universe from a placid, featureless expansion into a dynamic landscape of delayed violence. It reminds us that the peace of the present cosmos was hard-won, and that the very atoms in the oldest stars may carry chemical scars from the last skirmishes of the great matter-antimatter war. As our journey through these theories continues, hold this image close. A newborn cosmos still flickering with isolated annihilation flashes while fragile nuclei struggle to survive. A delicate dawn lit by the fading embers of a conflict whose outcome let there be light. Those annihilation blazes were just one face of a far larger family of cosmic pruning shears. A whole class of theories shares a simple, radical core. Long after the standard nuclear cooking was over, the infant universe was flooded with a thin but piercing background of non-thermal high-energy photons. These were not the gentle, fading glow of the cooling cosmos. They were outsiders born from processes that had nothing to do with the smooth thermal bath. They might have streamed from the decaying relics of dark matter, from the snapping cusps of cosmic strings, from evaporating microscopic black holes, or even from the first generation of cosmic rays catapulted by ancient magnetic shocks. The common thread is that this transient, high-energy light arrived as an afterthought, finding a universe already filled with freshly forged hydrogen, helium, deuterium, and a puzzling overabundance of lithium-7. And it arrived with exactly the right scissors to trim that overabundance without ripping the rest of the fabric. The scalpel is photodisintegration, a word that sounds clinical but describes a nuclear smash-up as precise as a key turning a lock. Every atomic nucleus sits at the bottom of a potential well, surrounded by energy walls. To break it apart, a photon must arrive carrying at least as much energy as the binding that holds the nucleus together. For sturdy helium-4, that wall is an imposing 20 megaelectronvolts, making it nearly immune to all but the most violent cosmic rays. For deuterium, the wall is far lower, only about 2.2 megaelectronvolts. Lithium-7 sits on a delicate perch with a binding energy just a sliver higher, roughly 2.5 megaelectronvolts. That tiny margin is the theoretical fulcrum on which the entire lithium problem can be pried loose. If the universe was bathed in a faint, late-arriving glow of photons with energies tuned just above that 2.5 million electronvolt threshold, they would find lithium-7 vulnerable. The photon would slam into the nucleus and split it into helium-4 and a triton, a heavy cousin of hydrogen. The lithium would be erased, but the slightly more fragile deuterium might remain untouched if the photon spectrum was soft enough, or if the photon bath was too thin to do widespread damage to deuterium's more abundant population. This is not a single model theory, but a vast umbrella. Under it gather many of the suspects we have already met. The decaying gravitino, the sterile neutrino that mixed just so, the primordial black hole that evaporated in a gamma-ray whisper, all of them are, in the end, photon injection machines. Their individual physics might be exotic, but their chemical weapon is the same late-time non-thermal glow. The power of this broader class lies in its universality. You do not need to pinpoint a single particle identity to test it. You can simply ask, what kind of post-nucleosynthesis radiation field would bring the lithium-7 prediction down by the required factor of 3 without bruising deuterium and helium beyond their observed bounds? The answer turns out to be a field that is soft, meaning dominated by photons just above the lithium-7 threshold, and that is relatively brief, switching on after the universe has expanded enough that deuterium has safely locked away inside helium and is no longer floating freely as an easy target. High-energy astrophysics enters this story from a different door. The same non-thermal photons that pruned lithium could have been spawned by the first cosmic rays in the universe. Picture the very first stars, colossal and short-lived, collapsing into black holes that launched ferocious jets. Or imagine the shock waves from the quark-hadron transition rippling through the thin haze of residual protons and electrons, acting as natural particle accelerators. These early cosmic rays, mostly protons and helium nuclei themselves, would have barreled through the sparse intergalactic medium, occasionally smashing into a stray proton. The collision would breed pions, which then decay into gamma-ray photons. That photon cascade would arrive minutes, hours, or even centuries after nucleosynthesis had formally ended, a delayed drizzle of destructive light. In this picture, the lithium erasure is not the work of dark matter at all, but the calling card of the universe's first high-energy engines, the primordial forges of non-thermal radiation that would later blossom into the blazing quasars and gamma-ray bursts we see in the modern sky. The beauty of this umbrella theory is its dual traceability. The same late photon bath that sculpted lithium would have left other marks. A faint spectral distortion in the cosmic microwave background, a tiny excess in the far infrared or soft gamma-ray sky, these are the lingering ashes. Observatories like the Fermi Gamma-Ray Space Telescope and future missions mapping the X-ray background are effectively hunting for the ghost of this ancient pruning light. Every new limit on a diffuse non-thermal glow from the first billion years tightens the parameters of the photon bath. If a future survey detects a subtle, soft gamma-ray excess exactly where nucleosynthesis models predict it should be, we would have direct proof that the lithium shortfall is a fossil of high-energy afterburn, and that the story of the first light elements is inextricably tied to the most violent accelerators the young universe could construct. It would mean that the gentle dawn of chemistry was, in truth, lit by a hidden and ferocious flashbulb, its afterglow still leaving a faint, warm scar on the background of the sky. No bomb, however, was as unforgiving as the quiet gate that had already opened minutes earlier. All the exotic pruning we have explored, from decaying gravitinos to late antimatter flashes, only works because a far older and more delicate valve had already set the raw proportions of the lightest elements. That valve was deuterium, and its formation was never a sure thing. It was a needle-thin passage balanced between two impossible extremes, a moment when the entire cosmos hung on the edge of a knife so sharp that a single percentage point of extra density or a whisper of extra heat could have flooded the universe with helium or left it a sterile sea of plain hydrogen. The gatekeeper role of deuterium cannot be overstated. Before a single atom of helium, lithium, or beryllium could form, the universe had to solve a chemical paradox. Two protons can meet and briefly stick, but the resulting nucleus, a pairing known as the diproton, is so violently unstable that it falls apart almost instantly in a shower of broken parts. The strong nuclear force simply cannot hold two protons together without a neutron to calm the electrical repulsion. That neutron is the crucial peacemaker, and when one finally binds to a single proton, the result is deuterium, a fragile couplet that stays together just long enough to serve as the stepping stone for everything else. But this creation came with a catch so brutal that it is often called the deuterium bottleneck. The very same universe that was trying to build deuterium was also boiling with high-energy photons, each one eager to smash it apart. The bottleneck is not a solid wall. It is a frantic war of construction and destruction waged at every cubic centimeter of the infant cosmos. The survival of deuterium boiled down to a single, breathlessly tight threshold temperature, roughly equivalent to the searing heat inside the core of our present-day sun. As long as the universe blazed above this mark, every deuterium nucleus that briefly flickered into existence was shattered by a photon almost before it could draw its first metaphorical breath. The nuclear chef was trying to sift flour in a hurricane. Only when cosmic expansion dragged the temperature below this critical value did the photon army lose its punch. The photons were still there in staggering numbers. Their energy per particle had simply fallen too low to pry the proton and neutron apart. That crossing was the true beginning of heavy element creation, the moment when deuterium at last began to accumulate in meaningful amounts and could start pairing into helium. Because this gate was so narrow, even a tiny deviation in the forces controlling it would have reshaped the whole periodic table. This is the heart of the deuterium bottleneck theory. Consider the background temperature as a general hand on a dimmer switch. If the universe had been just a fraction of a % warmer when it reached this bottleneck, the photon bath would have retained the power to destroy deuterium for a precious handful of moments longer. Those moments would have been catastrophic. Every minute of delay in clearing the bottleneck meant that more of the free neutrons, those precious ticking clocks we met earlier, would have decayed into protons. The neutron supply would have been further starved. When the bottleneck finally broke, there would simply not have been enough neutrons left to build helium-4 to the level we observe today. The universe would have emerged from its first hour a pale, helium-poor place, its star-forming future altered at a fundamental level. Conversely, if the temperature had dipped just slightly earlier, even by a degree, deuterium would have begun stockpiling sooner. The abundant neutrons would have been swept up into helium with almost reckless efficiency, leaving barely any deuterium to survive as a fossil signature. The delicate balance we actually measure, with roughly one deuterium atom remaining for every few tens of thousands of hydrogen atoms, is a middle ground so precise that many cosmologists view it as the single strongest evidence that the early expansion raced exactly as the Standard Model predicts. But the temperature was not the only trembling needle. The very reactions that built and broke deuterium were themselves governed by an intricate dance of cross-sections and resonance peaks, nuclear physics terms that describe the likelihood that two particles will stick. Even a microscopic change in the reaction rate of deuterium destruction, perhaps tweaked by a slightly different fine structure constant or a new force acting in the plasma, could have swung the elemental pendulum with terrifying force. Imagine the bottleneck as a sink drain with a small hole. The speed at which water flows out depends not just on the pressure of the water above, but on the exact diameter of that hole. If the hole is even a sliver wider, the drain runs too fast and the tub empties prematurely. If it is a hair narrower, the water pools and overflows in a completely different pattern. In the early universe, the water was the flood of free neutrons, and the drain was the deuterium destruction rate. A slightly faster destruction rate would have kept the bottleneck sealed until the universe became colder and emptier, resulting in fewer neutrons left to fuse and a barren helium output. A slightly slower destruction rate would have cracked the bottleneck open sooner, gobbling up neutrons into helium and leaving a deuterium abundance far smaller than what our telescopes measure in distant primordial clouds. This razor sensitivity makes deuterium the pressure-sensitive valve that constrains every exotic theory we have visited. Any idea that proposes a late injection of energy, like a decaying gravitino or early dark energy, must first prove that it does not alter the effective temperature or the destruction rate of deuterium during this crucial window. If a late decaying particle had dumped its energy too early, even by a few minutes, it would have reheated the photon bath and slammed the deuterium bottleneck shut again, annihilating the emerging supply of deuterium and throwing the entire helium census into disarray. The precision of the deuterium measurement has become the ultimate quality check on all new physics. To change the primordial lithium-7 by a factor of 3 without also jostling deuterium and helium beyond their observed narrow ranges, a theory must be exquisitely surgical. It must either act strictly after the bottleneck has fully cleared, once the deuterium has been safely stitched into helium, or it must act so gently that it shifts the destruction rate by an almost imperceptible amount, imperceptible yet still enough to trim a little lithium from the final broth. And that is precisely why the deuterium bottleneck theory is not just another item on a list. It is the fulcrum upon which the entire Big Bang nucleosynthesis pivots. It explains why helium-4 is so stubbornly robust once made, why lithium-7 might have been so easily and selectively erased by late photodisintegration, and why deuterium itself stands as the most precise baryometer in the cosmos, a living ruler that tells us how much ordinary matter truly exists. Every improved measurement of deuterium's absorption lines in front of ancient quasars is a direct measurement of the bottleneck's opening hours. Every numerical simulation that nudges the destruction cross-section up or down by a % is a stress test of the Standard Model's core. The fact that the observed deuterium abundance neatly aligns with the value inferred from the cosmic microwave background radiation is a quiet, steady triumph. It tells us that the gatekeeper did its job almost exactly as theory predicts, and yet the lithium shortfall keeps whispering that almost exactly may not be exactly enough. Perhaps the key to unlocking the lithium anomaly is not a new particle at all, but a deeper understanding of this single, delicate valve, a tiny, overlooked wrinkle in the deuterium destruction history that cosmologists have yet to fully see. The gatekeeper may still hold a secret, and every ancient photon sliding through a distant gas cloud is a note slipped under its door. That gatekeeper, however, rested its entire authority on a quiet and nearly invisible assumption. The Standard Model of nucleosynthesis, for all its breathtaking precision, is built on a vision of the early universe as a perfectly still, perfectly smooth thermal bath. Every photon, every proton, every neutron, every fleeting electron was presumed to dance to the exact same temperature, their speeds distributed along a single, peaceful bell curve that physicists call a Maxwellian distribution. In this serene picture, there are no stragglers, no sudden gusts of speed, no particles rocketing far ahead of the pack. The only thing that matters is the average heat of the crowd. The rates at which nuclei fuse, shatter, and stick are all calculated under the assumption that the entire cosmic kitchen is in flawless thermal equilibrium. And yet that assumption is not a law of nature. It is a mathematical convenience, a simplification that erases the genuine turbulence, the snapping magnetic fields, and the violent phase transitions that we already know were shaking the infant cosmos. The theory of non-thermal nuclear reactions tears up that serene bell curve and replaces it with a far more chaotic and feral reality. The idea is deceptively simple. In any real, churning plasma, the particles do not all march to the same drummer. Turbulent eddies, shock waves, and sudden releases of magnetic energy can kick a small fraction of particles into a frenzy, flinging them up to energies far beyond what the average temperature would allow. These outliers form what physicists call a high-energy tail, a thin but potent population of speed demons that slash through the quiet crowd. And when it comes to building or breaking atomic nuclei, a tiny handful of superthermal particles can do the work of an entire furnace. To grasp why, think of a calm lake on a windless morning. The water molecules everywhere share roughly the same slow, gentle motion. That is the thermal Maxwellian core. Now imagine skimming a single sharp stone across the surface. The ripple it kicks up is not part of the calm thermal ensemble. It is a localized, high-energy disturbance that can jar a floating leaf loose or crack a thin sheet of ice in ways the still water never could. In the early universe, the stones were events like magnetic reconnection. When primordial magnetic field lines, twisted and tangled by swirling plasma flows, suddenly snapped and reconnected, they released bursts of energy that could accelerate protons and neutrons to speeds far exceeding the thermal average. The gentle, uniform temperature that governs the deuterium bottleneck was in these pockets no longer the whole story. A single proton rocketing out of a magnetic reconnection flare could slam into a deuterium nucleus with such force that it overcomes the electrical barrier far earlier than the average particle could, effectively altering the local fusion rate on the spot. The same logic applies to turbulence left over from the quark-hadron phase transition. We have already explored the violent bubbling that might have accompanied the freezing of quarks into protons and neutrons. Those density shocks and expanding phase walls did not just sort matter into clumps, they also stirred the plasma into a froth of chaotic motion. Turbulence, whether in a cup of coffee or in a newborn universe, is a machine for creating extreme events. The swirling eddies generate local hotspots and thin streams of particles that collide head-on with energies far outside the smooth thermal envelope. The consequences of these high-energy tails for nucleosynthesis are profound and deeply selective. The standard reaction rate calculations assume that fusion only happens when two particles in the quiet bulk of the bell curve happen to meet with just enough energy. But the tail particles are already carrying extra punch. They can tunnel through the electrical repulsion barrier more easily, triggering reactions at a faster clip even if the overall cosmic temperature had already dropped below the usual threshold. This means that the deuterium bottleneck, that delicate gate we have so closely guarded, could have been pried open in localized spurts by non-thermal protons smashing into neutrons before the average photon bath was ready. Deuterium might have begun accumulating in small, scattered patches earlier than the smooth model predicts. Conversely, the same high-energy protons and alpha particles could have acted as tiny demolition crews. A proton with a non-thermal energy boost can smash into a fragile lithium-7 nucleus and break it apart, even if the ambient photon temperature is too cool to do so. This introduces a new lithium destruction channel that operates entirely through particle collisions rather than photon shattering. And because the tail population is so sensitive to the local magnetic and turbulent landscape, the lithium pruning would be sporadic and patchy, varying from one pocket of the early universe to the next. This offers a fresh and compelling angle on the stubborn lithium problem. In the standard picture, the universe-wide average of lithium-7 is much too high. But if non-thermal reactions were at work, the lithium destruction would have been focused in the most turbulent regions, the places where magnetic fields snapped hardest and where phase transition shocks left the deepest scars. The ancient stars we observe today might simply trace gas that condensed from those battered pockets, chemically scoured of lithium, while other, quieter patches retain the full primordial overabundance. The low and uniform lithium plateau in halo stars would then be a selection effect, a biased sample drawn from the most magnetically active regions of the early fireball. Crucially, this non-thermal scalpel can be tuned to spare helium and deuterium. Helium-4 is a nuclear fortress, its binding energy so high that even a super-thermal proton cannot easily scratch it. Deuterium is more vulnerable, but the non-thermal tail can be shaped. If the accelerating mechanism, say magnetic reconnection, preferentially boosts protons to a specific energy range, it will trigger lithium destruction while leaving deuterium largely untouched. This is not a blunt hammer but a frequency-tuned instrument, and its tuning dials are the strength and structure of the primordial magnetic fields and the violence of the turbulent cascade itself. The testability of this theory ties it back to the same intergalactic magnetic fossils we have already invoked. A universe threaded with strong enough primordial fields to drive non-thermal nucleosynthesis would also leave a distinct magnetic signature in the voids between galaxy clusters today. Future radio telescopes mapping the faint Faraday rotation of light passing through these voids can measure the strength and coherence of these ancient fields, providing a direct cross-check on whether the turbulent tail was truly active during the first 3 minutes. Furthermore, laboratory experiments that recreate turbulent plasma conditions in magnetic confinement fusion devices are already studying how non-thermal tails affect reaction rates, offering a miniature, modern echo of the primordial kitchen. This line of thinking challenges the very foundations of our cosmic story. It tells us that the early universe was not a placid, well-stirred pot gently cooling on a stove. It was a wild, writhing storm where invisible magnetic strings snapped and rang, where density shocks carved deep currents, and where a thin, hot blade of outlier particles sliced through the quiet thermal crowd, silently rewriting the chemical destiny of the cosmos. The lithium shortfall might therefore be more than a mismatch in an equation. It could be the statistical shadow of a chaotic dawn, a whisper that the first atoms were forged not in silent equilibrium, but in a maelstrom of non-thermal fury that we are only just beginning to understand. The forces that held the first atoms together were never fixed. A ghostly, shape-shifting field may have threaded the newborn cosmos, silently bending the very glue that binds protons and neutrons. This is the chameleon field, a scalar field whose entire personality shifts depending on the density of its surroundings. In the deep emptiness of modern intergalactic space, it would be a long, light, almost unfeelable whisper, allowing it to drive the accelerating expansion of the universe as a form of dark energy. But plunge it into the searing, crowded nuclear broth of the early universe, and its mass would swell. It would become a short, heavy, hidden hand, gripping ordinary matter so gently that we have never caught it in a laboratory, yet strongly enough to twist the delicate nuclear reaction rates that forged the first light elements. A chameleon field works like a creature that darkens against a shaded rock and pales on open sand, except its backdrop is the density of matter itself. In a dense environment, the field's effective mass grows large, its influence becomes tightly localized, and it hides from view. In a sparse environment, its mass shrinks, its reach extends, and it spills across the cosmos as a subtle, repulsive energy. This density-sensitive coupling gives it an almost magical selectivity. A chameleon field would have left the later, thinner universe almost untouched, avoiding the tight constraints of precision gravity tests within the solar system. But in the crushing press of the first few minutes, where baryon densities were millions of times richer than anything we see today, the field would have been awake and active, coupling directly to protons and neutrons and altering their effective masses and binding energies. Nuclear binding energies are the delicate springs that govern every fusion and photo-shattering step we have explored. Even a tiny nudge in the binding of deuterium would have shifted the temperature at which its fragile bottleneck broke open. A slightly stronger deuterium bond, and the nucleus could have survived a hotter photon bath, unlocking the gate earlier and changing how much deuterium survived to become helium. A slightly weaker bond and the bottleneck would have lingered, starving the neutron supply. The chameleon field would not have applied this nudge uniformly, because its influence depended on the local matter density, and because the young universe was already rippled with density variations from quantum fluctuations. The field would have varied in strength from one patch of space to the next. Some pockets denser and richer in baryons would have felt a heavier chameleon with a different effective coupling. Other pockets, slightly thinner, would have experienced a lighter, more diabolic version. The result was not a single, universal shift in nuclear physics, but a shimmering, three-dimensional quilt of varying reaction rates. This spatial quilt writes itself directly into the pattern of primordial abundances. In a pocket where the chameleon field strengthened the binding of lithium-7, that nucleus would have been harder to photodisintegrate and more readily produced, creating a local lithium excess. In another pocket where the field weakened the crucial beryllium-7 formation pathway, the lithium yield would have been pruned just as effectively as any decaying particle could manage, but through a shift in fusion rather than late-time destruction. Crucially, because the chameleon field's coupling to protons and neutrons is so specific, it can be tuned to sculpt the problematic lithium-7 while leaving helium-4 and deuterium almost untouched in the spatially averaged senses. The same field that erases lithium excess in one region might leave a faint deuterium surplus in another, but when integrated across all the gas that later formed the first stars, the net average could still satisfy the tight observational bounds we have discussed. This leads to a stunning and testable prediction: a genuine spatial scatter in the light element abundances. A chameleon field would imprint a unique, density-correlated fingerprint on the primordial metal-poor halo stars. Rather than finding a flat, universal lithium plateau in every ancient star across the galactic halo, astronomers would see a subtle but genuine variation, a scatter that correlates with the expected local baryon density of each star's birth cloud. The stars that condensed from denser knots of early gas would carry one lithium signature, while those born from thinner, emptier voids would carry another. Current surveys of halo star lithium are already hinting at a small but persistent dispersion beyond what standard stellar atmospheric modeling can explain. A chameleon field would turn that anecdotal scatter into a systematic, predictable map. It would link the terrestrial measurement of a spectral line in a distant stellar atmosphere directly to the ambient density of the early universe in its immediate neighborhood, a connection almost inconceivably intimate. The chameleon also threads a path back to the deepest cosmic puzzle. This same scalar field, if it exists, would be the dark energy accelerating the modern expansion of space. The mystery of the lithium shortfall and the mystery of why the universe is now blowing apart at an ever-increasing rate might have a single shared origin. The chameleon field, massive and hidden in the early dense era, would have silently fine-tuned the nuclear furnace without revealing itself to later tests of gravity. Today, in the ultra-thin vacuum of the cosmos, it becomes the low-mass driver of a gentle cosmic push, its very lightness masking it from laboratory searches that probe only dense environments. Experiments designed to test chameleon models are already underway, from delicate measurements of the Casimir force in vacuum chambers to atom interferometry that senses tiny deviations from Newtonian gravity. Any detection would not just confirm a new particle, it would simultaneously pierce the veil on the elemental alchemy of creation, demonstrating that the chemistry of the first 3 minutes was choreographed by a field that still ripples through the dark expanses between galaxies, shaping the fate of the universe from its violent birth to its final, frozen end. Ancient stars are not the perfect time capsules we assumed. Every one of those metal-poor halo beacons that astronomers have so carefully measured may in fact be a slowly fading chemical photograph, a picture that has been quietly bleaching for more than 13 billion years. The lithium problem that has haunted cosmology might not be a glitch in the Big Bang at all. It could be a story of patient, invisible erosion, an astrophysical thief at work inside the stars themselves. And if that is true, then the standard model of nucleosynthesis is not broken. It is simply waiting for us to learn how to read the stars correctly. The assumption has always been that the surfaces of ancient stars faithfully preserve the elemental mix of the primordial gas from which they condensed. These stars, born before the galaxy had been polluted by supernova iron, were thought to carry their original lithium abundance like a birthmark, unaltered and pristine. But a star is not a cold museum case. It is a roiling, turbulent engine, and over billions of years, even the gentlest internal currents can slowly shuffle the elements from its surface down into its deep, hot interior where lithium cannot survive. This is the theory of stellar lithium depletion, and it offers a startlingly clean solution to the whole puzzle. The Big Bang produced exactly the lithium the equations predict, but the oldest stars have been hiding it, or rather destroying it, ever since. The most pervasive of these internal sculptors is diffusion. The atoms inside a star are not frozen in place. They are swimming in a fierce bath of gravity and radiation. Heavier elements, including lithium, feel the tiniest extra downward tug compared to hydrogen and helium. Over cosmic timescales, this microscopic nudge causes lithium atoms to sink, drifting slowly out of the visible photosphere and into the deeper layers where the temperature soars past 2 million degrees. At those temperatures, lithium is dismantled instantly. A proton will slam into a lithium-7 nucleus and split it into 2 helium-4 fragments. The lithium atom is not just hidden. It is erased from existence. From our telescopes gazing at the star's surface, the lithium appears to have simply vanished, leaving behind a fainter spectral fingerprint than the primordial gas ever contained. Rotational mixing accelerates this erasure into a steady downward churn. Stars are born spinning, and the oldest stars, those pristine messengers from the early galaxy, were often rapid rotators in their youth. Rotation drives gentle but persistent circulation currents, huge meridional flows that loop from the equator to the poles and back again, dragging surface material down into the star like a slow conveyor belt. Any lithium riding that conveyor belt is carried into the destruction zone and consumed. At the same time, turbulence generated by the same spinning motion can stir the star's interior, constantly feeding fresh surface gas into the furnace while bringing lithium-poor gas back up to masquerade as the original photosphere. Over billions of years, even a mild rotation can scrub the surface lithium down to a small fraction of its birth value. Mass loss adds yet another layer of disguise. The earliest stars, lacking the heavy elements that make modern stellar winds efficient, were not static. They could shed material through pulsations, flares, or gentle winds driven by magnetic activity. When an ancient star puffed away its outermost envelope, it exposed deeper lithium-poor layers that had already been partially processed. The atmosphere we measure today might not be the surface the star was born with. It could be a chemically stripped core, a survivor that has already lost its original lithium-laden skin into the surrounding void. The lithium atoms are not necessarily destroyed in this scenario. They are simply scattered into the interstellar medium, diluted into a sea of gas so vast that we can no longer trace them back to any single star. None of these processes are wild speculation. They are the very same mechanisms that explain a much closer cosmic puzzle, the solar lithium problem. Our own sun, a middle-aged star born with what should have been a modest lithium supply, now shows a photosphere with less than 1% of the lithium found in the meteorites that formed alongside it. The sun has not been still. Diffusion and rotational mixing have been busily settling and destroying its lithium for 4.5 billion years, and the effect is striking and undeniable. If our own calm, middle-aged star can hide nearly all of its lithium in such a short cosmic span, imagine what a violent, fast-spinning first-generation star might accomplish over more than 13 billion years. The lithium plateau that astronomers measure in ancient halo stars might not be a record of the primordial abundance at all. It could be a depletion floor, the lowest level that these processes can drive the lithium down to before other physics halts the destruction. This shifts the lithium problem from cosmology to stellar physics. The task is no longer to invent new particles or alter the fundamental constants. It is to build more precise models of how lithium diffuses, how rotation mixes, and how mass loss peels away the outer layers of the oldest stars. Researchers are already doing this, weaving together three-dimensional hydrodynamic simulations with detailed nuclear burning networks to track the fate of a single lithium atom from a star's turbulent birth to its quiet old age. The results so far are promising but cautious. They show that diffusion alone can deplete lithium by a factor of 2 or more across the lifetime of a typical halo star. When rotational mixing is introduced, the depletion can easily reach the factor of 3 needed to erase the cosmological discrepancy entirely. The challenge is that these models are exquisitely sensitive to slightly uncertain parameters: the precise profile of the internal rotation, the efficiency of the mixing currents, the strength of the atomic settling. A small tweak can tip the predicted depletion from too little to too much, and the models must also not spoil the observed abundances of other fragile elements like beryllium and boron, which are also susceptible to destruction at slightly different depths. The most captivating evidence for an astrophysical solution lies not in a single star but in the subtle scatter we are beginning to uncover. For decades, the lithium plateau was seen as a flat, unwavering line. But as telescope spectrographs have grown more sensitive, astronomers have started to detect a faint but real spread in the lithium abundances of otherwise identical halo stars. Some show slightly more lithium, some slightly less, and the spread seems to grow as stars become hotter and more massive, exactly the pattern expected if internal mixing is more vigorous in faster spinning, more turbulent stellar interiors. This scatter is incredibly hard to explain if the lithium abundance is purely primordial and universal, but it becomes perfectly natural if we are watching different stars from the same generation at different stages in their lithium destruction, each one a snapshot of a slow, ongoing leak. One deep implication of this theory is profoundly reassuring. The Big Bang might be innocent. The beautiful concordance between the helium-4 and deuterium measurements and the standard model of nucleosynthesis would stand untarnished. The cosmic kitchen that cooked those elements did its job perfectly. Lithium is simply the one ingredient that cannot survive its own vessel. The very stars we rely on to weigh the primordial fire are, in this view, cracked ceramic cups that slowly spill their contents over a lifetime longer than the current age of the universe. The lithium shortfall is not a scream for new physics but a quiet lesson in stellar humility, reminding us that a star is a living thing that processes, hides, and erases the very atoms we seek to measure. The coming years will sharpen this blade dramatically. The European Space Agency's Gaia satellite has already mapped the exact distances and motions of millions of stars, allowing astronomers to identify the oldest, least contaminated halo members with unprecedented precision. Next-generation spectrographs on extremely large telescopes will peer at those stars and measure not just lithium, but also the isotopic ratio of lithium-6 to lithium-7 in their atmospheres. That ratio is a subtle but powerful clock because lithium-6 is destroyed at a lower temperature than lithium-7. If stellar depletion is the culprit, the ratio will be shifted in a telltale way, pointing directly to an internal furnace rather than a cosmic shortfall. If such a signature is found, the lithium problem will not so much be solved as dissolved. It will transform into a new, rich chapter in the story of how the earliest stars lived, spun, and breathed their elements back into the void, leaving only a faded chemical whisper of the perfect primordial dawn that actually was. The lithium anomaly was not the only crack that once seemed to split the standard cosmic model. Deep in the heart of Big Bang theory lies a single number that should be the same no matter which door you enter through. That number is the baryon density, the total count of ordinary matter protons and neutrons packed into every cubic meter of the infant universe. It is the master dial that sets the entire elemental recipe. For decades, cosmologists had two entirely independent ways of measuring it, and for a long, uncomfortable stretch, the two measurements refused to shake hands. The tension was not a minor squabble over decimal points. It was a genuine inconsistency that threatened to topple the elegant tower of standard nucleosynthesis. The first doorway was the cosmic microwave background, the oldest light in the sky. The pattern of hot and cold spots in that fossil glow is a fingerprint of the primordial plasma, and the relative heights of its acoustic peaks encode the baryon density with stunning precision. The second doorway was the chemical fossil record, specifically the abundance of deuterium left over from the Big Bang. Deuterium is the most sensitive baryometer in the cosmos. If the universe was thick with protons and neutrons, the press of particles would have burned deuterium into helium with ruthless efficiency, leaving a scant remnant behind. If the universe was thin, deuterium would have escaped the blaze more easily, and its surviving fraction would be higher. In the 1990s and early 2000s, these two doors led to different rooms. The deuterium measurements from distant pristine gas clouds, backlit by bright quasars, pointed to a baryon density that was noticeably lower than the one emerging from the first high-fidelity maps of the microwave sky. The discrepancy was not enormous, just a few parts in 10 billion, but it was sharp enough to make the paint peel. If the deuterium baryometer was correct, then the standard model of nucleosynthesis was cooking with too much heat. The prediction for helium-4 would nudge upward or downward in ways that strained the observations. The lithium problem, already a headache, would shift in unpredictable directions depending on which baryon density you trusted. The whole delicate interlocking chain of light element predictions suddenly seemed to dangle from a frayed rope. This tension became a fertile field for new ideas. It spurred a burst of non-standard nucleosynthesis theories. If the baryon density inferred from deuterium was truly at odds with that from the cosmic microwave background, then perhaps the foundational assumptions were wrong. Maybe the universe was not quite as smooth as the standard model assumed, and the patchy quark-hadron transition we explored earlier could have tilted local deuterium production. Maybe an extra family of neutrinos was silently adding energy to the expansion, fooling the baryometers. Or perhaps a chameleon field was subtly warping the binding energies of the light nuclei, shifting deuterium's survival rate without leaving a fingerprint on the microwave sky. Every one of the exotic theories we have journeyed through was in part nourished by this crack in the numbers, but the seed of the solution was already growing. The cosmic microwave background measurements were improving at a headlong pace. The Wilkinson microwave anisotropy probe, called WMAP, flew in 2001 and sharpened the acoustic peak heights into a razor line. The baryon density from WMAP drifted upward, edging toward the deuterium value. Then came the Planck satellite, launched in 2009, which mapped the primordial glow with such fine-grained precision that its measurement of the baryon density became a gold standard. Simultaneously, astronomers were hunting deuterium in ever more pristine, untouched gas clouds, using the spectrographs on the largest telescopes on Earth and in space. The noise bars shrank, the systematic errors in the chemical measurements were wrung out one by one. The two numbers converged. Today, the baryon density inferred from deuterium in intergalactic clouds and the baryon density extracted from Planck's exquisite acoustic maps are in near-flawless accord, both pointing to a value of about 6 parts in 10 billion. It is a quiet, profound triumph. The standard model of nucleosynthesis, with just 3 neutrinos and a smooth, unmodified expansion, can simultaneously account for the deuterium in ancient gas, the helium in pristine galaxies, and the cosmic microwave background fluctuations using a single, unified number. That convergence is one of the strongest pillars of modern cosmology. It tells us that the cosmic kitchen, in its broad strokes, is understood with almost spooky precision. And yet, a subtle ghost still stirs. The convergence is not absolute. The very latest analyses reveal a tiny, persistent murmur, a shadow of the old tension. The deuterium measurements, while now tightly clustered, still cluster at a value that is a slight breath lower than the central Planck baryon density, a difference of perhaps 1 or 2%. Some astronomers argue that this whisper is nothing more than an unaccounted systematic, a tiny fraction of deuterium hiding in dust grains or a subtle misestimate of the gas temperature in those distant clouds. Others wonder if it is the last faint voice of new physics, a hint that the expansion rate during nucleosynthesis was ever so slightly different from the standard assumption, perhaps nudged by a sterile neutrino that barely mixed or by a magnetic field that subtly strained the photon bath. The lithium problem lingers in the corner of this conversation because lithium-7 is also a baryometer, albeit a far flakier one. If you force the baryon density to exactly match the microwave background, the lithium discrepancy grows as large as ever. If you let the baryon density drift a tiny bit toward the deuterium value, the lithium shortfall eases just a little, but it does not vanish. The alignment of the baryon density from two great cosmic pillars has therefore not killed the need for deeper understanding. It has simply reshaped the question. The era of a glaring, crisis-level baryon inconsistency is over. In its place stands a far more subtle and tantalizing puzzle, a nearly perfect agreement with just enough wiggle room to keep the door ajar for a hidden sector. The delicate dance between deuterium and the microwave background is not just a dry consistency check. It is the very clamp that holds the standard model together, and the very lever that will one day pry it open if that 1 or 2% whisper proves to be not an error but a genuine new signal from the depths of the first 3 minutes. A ghostly sea of primordial neutrinos still washes through your body. Every cubic centimeter of space, right down to the gap between your fingers, hums with a faint, silent rain of particles that have not touched matter since the universe was 1 second old. The cosmic neutrino background is not a speculative extra. It is a stone-cold prediction of standard Big Bang physics, as inevitable as the afterglow of the microwave sky. In that blistering opening second, while the cosmos was still a thick, opaque soup of protons, electrons, and light, neutrinos were already slipping loose. They decoupled and streamed away, carrying with them a snapshot of the universe at a temperature of 10 billion degrees. Today, that snapshot survives as a bath of ghostly particles cooled by cosmic expansion to a whisper just above absolute zero. But we have never caught one. No detector has ever felt the faint kick of a primordial neutrino, and yet we know that C is there, and we know its temperature, its density, and its silent power, because the first light elements recorded it with a chemist's precision. The bridge between a neutrino that passed through you a moment ago and a helium nucleus forged 13 billion years ago is direct and unforgiving. Those ancient neutrinos did not just drift away as passive relics. They were full partners in the expansion dance, contributing a stiff radiation pressure that pushed the universe apart faster. The energy they carried is locked into a single number, the effective number of neutrino species, a parameter that counts how many relativistic degrees of freedom were buzzing through the plasma. In the standard picture, with 3 flavors of light neutrinos, that number lands just a hair over 3, because the electrons and positrons that later vanished dumped a little extra heat into the photons, but not into the already decoupled neutrinos. That tiny asymmetry, that slight warmth, is the fingerprint of a cosmos doing exactly what the equations demand. If the effective number of neutrino species had been different, if even a single extra sterile neutrino had been present and fully thermalized, the whole metronome of the first 3 minutes would have shifted. More radiation energy means a faster expansion. A faster expansion means the weak interactions that transform protons into neutrons froze out at a hotter moment, locking in a higher neutron fraction. That surplus of neutrons would have cascaded directly into more helium-4 and left a different mark on deuterium. The primordial helium abundance is a razor-sharp neutrino counter. Raise the effective number by just 1 extra neutrino, and the helium mass fraction swells by nearly a full percentage point, a shift so large that telescopes peering at pristine gas clouds would have spotted it decades ago. The fact that those measurements cluster tightly around the standard value, roughly 24.7%, tells us that the neutrino C in the first second was almost exactly as quiet and simple as the textbook describes. But almost exactly is a loaded phrase. The very tightness of the helium and deuterium measurements transforms the light elements into the finest neutrino telescope ever conceived, one that peers not across space but back to the first second of time. Every subtle deviation in the expected neutrino energy density, whether from a sterile neutrino that mixed only weakly, from a hidden sector that funneled energy into dark radiation, or from a primordial neutrino-antineutrino asymmetry, would leave a chemical scar on the elemental senses. This is the true power of framing the light elements as an indirect detection of the cosmic neutrino background. We are not just checking a box in a textbook. We are using the nuclei forged in the baby universe as a calorimeter that weighed the entire ghostly sea. The deuterium bottleneck, that fragile gate that opened when the universe was just cool enough, is particularly sensitive to the neutrino tally because the expansion tempo governs how fast the universe cooled through that threshold. Slightly more neutrinos and the cooling was faster, the bottleneck broke differently, and deuterium survived in a subtly altered amount. The deuterium measurement from ancient quasar shadows is, in this sense, a direct readout of the neutrino background's energy pressure. This cosmic neutrino telescope has already caught whispers of possible new physics. The most recent fits from the Planck satellite and ground-based microwave telescopes, combined with the light element abundances, point to an effective neutrino number nuzzling just below the canonical 3, perhaps near 2.8 or 2.9. The statistical error bars still comfortably embrace the standard value, but the central drift has been persistent enough to make theorists lean forward. A number lower than 3 would be as startling as a number higher. It would imply that the early universe was missing some radiation energy, perhaps because the electron-positron annihilation delivered less heat to the photons than computed, or because some non-standard process drew a little energy away even earlier. If the drift toward 2.8 solidifies, it would demand a genuine revision, not a wholesale demolition of the standard thermal history. It might signal that the neutrino background is not perfectly thermal, or that a subtle asymmetry between neutrinos and antineutrinos changed the pressure during the deuterium opening. These are not idle fantasies. They are the exact kinds of distortions that would arise from a new force coupling to neutrinos in the first fractions of a second, a hidden gauge boson that nudged the thermal bath without ever touching a proton. And then there is the direct detection dream. At some point in the coming decades, a laboratory experiment like the Princeton Tritium Observatory for Light, Early Universe Massive Neutrino Yield, known as TOLMI, aims to capture the cosmic neutrino background directly by watching for the tiny energy kick a relic neutrino gives to a tritium nucleus. That experiment, if it succeeds, will measure the absolute temperature and density of the primordial neutrino sea with its own hands. The light element abundances and the TOLMI signal will then become a sealed loop, a cross-calibration spanning the entire history of the cosmos. If the neutrino energy density inferred from ancient helium agrees perfectly with the rain of neutrinos caught in a laboratory tank, we will have closed the book on a 40-year chase. If they disagree, if the chemical neutrino telescope shows a different energy than the direct one, then the gap between them will be the smoking gun of a new particle, a new field, or a new law of thermodynamics active only in the first seconds. So every time an astronomer refines the helium abundance in a distant dwarf galaxy, every time a spectrograph sharpens the deuterium lines in a quasar shadow, they are not just polishing old numbers. They are tightening the focus on a neutrino telescope aimed at the very edge of existence. The first light elements are the only surviving trace of that ghostly sea, a chemical record that fills the gap between the invisible neutrino background and the visible cosmic microwave sky. They tell us that the silent, weightless particles gliding through your body right now are not strangers. They are messengers from the first second, and the atoms that make you are the paper on which their message was written. Beyond the ghostly sea of neutrinos, another chemical whisper has been nudging at the edges of detection for years. Helium-3 is the overlooked sibling in the light element family, a rare isotope with just 2 protons and 1 lonely neutron. Unlike its chunky brother Helium-4, which flooded the early universe in staggering abundance, Helium-3 was forged only in the barest trickle during the first 3 minutes. The Standard Model predicts its primordial yield with extreme precision, roughly 1 helium-3 nucleus for every 10,000 hydrogen atoms. For a long while, that prediction sat quietly unchallenged, a footnote in the grand elemental census. But as radio telescopes grew sharper and began to map the faint spectral whispers of helium-3 in the Milky Way and nearby galaxies, a quiet discordance began to surface. The measured helium-3 tally in some galactic regions does not line up with the primordial recipe, and that small mismatch opens a door onto a whole new layer of cosmic chemistry that unfolds long after the first 3 minutes are over. To understand why this matters, you have to grasp the strange double life of helium-3. It is not just a primordial fossil, it is also a fragile currency exchanged between stars. When a low-mass star like our Sun enters its old age, swelling into a red giant, it dredges up material from its deep interior. In that deep furnace, some of the original deuterium and a fraction of the hydrogen can fuse into helium-3, which then rides convection currents up to the stellar surface. When the star finally shrugs off its outer envelope into a planetary nebula, that freshly minted helium-3 spills into the interstellar gas. At the same time, other stellar engines actively destroy the isotope. Massive stars burn helium-3 voraciously in their hot cores, and when they explode as supernova, they pump helium-3 pour gas back into the galaxy. The net abundance we measure in a given cloud is therefore not a clean primordial signal. It is a running balance sheet, a tug of war between stars that make helium-3 and stars that devour it, all happening across billions of years of galactic history. This means the helium-3 abundance is not a closed book. The standard Big Bang model tells us the starting capital, the total endowment of helium-3 deposited in the universe before the first star ever shone. But every generation of stars since then has been tinkering with the books, adding and subtracting in ways that vary from region to region. The mystery lies in the fact that some of the measurements, particularly from bright clouds of ionized hydrogen in our galaxy and its neighbors, show a helium-3 abundance that stubbornly exceeds what the primordial budget plus standard stellar processing can comfortably explain. In a few pockets, the isotope appears too abundant, as though an extra hidden source has been quietly injecting helium-3 into the gas over cosmic time. In other regions, the levels are surprisingly low, suggesting an efficient, unseen destruction pathway. Neither extreme fits the clean narrative of a single primordial seed followed by predictable stellar gardening. Low-mass stars are the main suspects in the excess. In the 1990s, astronomers used the Very Large Array radio telescope in New Mexico to measure the hyperfine line of helium-3. A faint radio emission at 3.2 GHz that acts as a unique beacon for the isotope. They found that some planetary nebulae, the puffed-off skins of dying sun-like stars, were gushing helium-3 into space at rates that seemed too generous by a factor of 2 or 3. If a significant fraction of all low-mass stars behave this way, then the interstellar helium-3 should gradually climb over the eons. That slow climb would mean that the abundance we measure in the modern galaxy is not a direct window into the Big Bang at all, but a locally inflated value shaped by the cumulative breath of trillions of aging stars. The primordial baseline would be masked by a thick patina of later production, forcing cosmologists to carefully peel back the layers before they can compare any measurement to the standard model. A competing twist comes from the destruction side. Stars more than about 3 times the mass of the Sun burn helium-3 so efficiently in their cores that they can almost completely erase the isotope from the gas they later return to the galaxy. If supernova-driven mixing is more thorough than models assume, Then the inner Milky Way, where massive stars have lived and died in great numbers for billions of years, should show a helium-3 deficit. That deficit has indeed been observed. The galactic center region, a graveyard of countless massive stellar explosions, is unexpectedly barren of helium-3. This creates a grand galactic gradient, an isotope map where the outer quiet suburbs retain a richer primordial signature while the violent downtown core has been chemically scrubbed clean. The mismatch with standard predictions is therefore not a single discrepancy but a spatial pattern, a chemical geography that hints at a far more turbulent and creative story of element evolution than the gentle, one-size-fits-all picture of simple cooling. Cosmic rays add yet another tool to the ledger book. High-energy protons zipping through interstellar space can occasionally smash into a helium-4 nucleus and chip off a neutron, transforming it directly into helium-3. This spallation process is not a major contributor, but it provides a steady, diffuse drizzle of fresh isotope that does not come from stars at all. It comes from the kinetic fury of ancient supernova shock waves still rattling through the galaxy. Conversely, a cosmic ray helium-3 nucleus itself can be shattered by a subsequent collision, turning destruction and production into a continuous, messy cycle. Every time astronomers refine their measurements of the cosmic ray spectrum, they are indirectly refining the correction factor needed to read the true primordial helium-3 signature beneath the noise of the subsequent billions of years. What makes the helium-3 anomaly so potent is that it is not a clean, showy crisis like the lithium problem. It is a slow-burning, subtle wobble that tests exactly how well we understand the entire interval between the first 3 minutes and the present day. Fixing the discrepancy does not require a new particle or a modified gravity. It demands a far more meticulous history of the galaxy itself, a reconstruction of every star that has lived, every supernova that has echoed, and every gentle stellar wind that has ever exhaled helium-3 into the void. This is a fundamentally messy, astrophysical puzzle rather than a pristine cosmological one, and that is precisely why it adds such a rich layer of complexity to the light element story. It reminds us that the atoms we measure in the modern universe have been processed, shuffled, cooked, and reprocessed through a cascade of stellar furnaces, and that the faint primordial signal we seek is buried under a palimpsest of galactic memories. Future telescopes will crack this open further. The next generation of centimeter-wave radio arrays with vastly improved sensitivity will map helium-3 across hundreds of nearby galaxies, not just our own. By comparing the isotope's abundance in galaxies of different ages, shapes, and star formation histories, astronomers can tease apart the primordial baseline from the later stellar noise. Each galaxy becomes its own experiment, a separate chemical laboratory where the starting helium-3 endowment has been subjected to a different history of stellar baking and cosmic ray battering. The grand hope is that beneath all that noise, a single, universal primordial value will emerge, one that either confirms the standard Big Bang prediction perfectly or nudges it by a slim, telling percentage. Either way, the helium-3 abundance mystery stands as a quiet, stubborn reminder that the first light elements did not simply freeze into stillness. They entered a 14-billion-year saga of creation, destruction, and transformation that is still being written in the faint radio whispers threading through the space between the stars. The deepest assumption of all was that the cosmos expanded evenly in every direction. For decades, Big Bang cosmology has been built on a quiet pillar known as the cosmological principle, the notion that the universe on the largest scales is both the same everywhere and the same in all directions. That principle is the reason we can talk about a single cosmic temperature, a single Hubble rate, and a single set of elemental abundances that apply to the entire sky. But what if, in the first few minutes, that pillar was nothing more than a mirage? A brief but radical departure from smoothness, an era when the young universe stretched far more fiercely along one axis than another, would have shattered the simplicity of the standard kitchen and written a hidden geography into the very atoms we measure today. This is the anisotropic universe model, and it suggests that the first light elements might carry a directional scar, a subtle compass pointing back to the wild geometry of the newborn cosmos. To understand how such a lopsided beginning could work, think of a giant rubber sheet being pulled from its edges. In a perfectly uniform cosmos, every tug is identical, and the sheet stretches outward in a perfect circle. That is the isotropic expansion we assume, a single Hubble rate governing every point and every direction. An anisotropic universe, by contrast, is like a sheet yanked far harder along one diagonal than the other. Space itself expands faster in one direction, while the perpendicular directions lag behind. This means the cosmic clock was not a single metronome but a set of racing and dawdling tempos depending on which way you faced. In the first seconds and minutes, this directional stretching would have been far more than a geometric curiosity. It would have reached deep into the physics of particle freeze-out and nuclear reaction rates, rewriting the local recipe for the first light elements. The key, as always, is the neutron. Recall that the proportion of neutrons to protons was locked in when the universe was about 1 second old, the moment neutrinos decoupled and the weak interactions that swapped protons and neutrons froze out. That freeze-out temperature depended exquisitely on how fast space was expanding. A faster expansion meant a hotter freeze-out, which preserved a touch more neutrons. A slower expansion meant a cooler freeze-out, tilting the seesaw slightly toward the lighter proton. In an anisotropic universe, the freeze-out was not a single global event. Along the direction of furious stretch, the cosmos raced through the critical temperature band a beat sooner, locking in a slightly different neutron fraction than in the direction where the expansion was more sluggish. The universe, in other words, was sprinkled with a directional neutron gradient, a gentle but real variation in the very seed material for all subsequent element building. That directional neutron seed would have cascaded directly into the abundances of helium, deuterium, and lithium. A patch of sky aligned with the fast axis, where neutrons were a bit more plentiful, would have cooked slightly more helium-4 and burned away a little more deuterium in the furious fusion that followed. A patch aligned with the slow axis, where neutrons were scarcer, would have produced less helium and left a richer residue of deuterium. The lithium-7 yield, already poised on a knife edge, would have been especially sensitive to this uneven start. Even a few % more neutrons in a given direction could have tipped the fragile beryllium-7 pathway into overproduction, while the opposite hemisphere might have seen lithium pruned exactly toward the lower values we observe in ancient stars. The lithium problem, in this view, might not be a universal shortfall at all. It might be a local measurement, a chemical snapshot taken from a region of the galaxy that condensed from gas tilted along a particular cosmic axis. The most astonishing prediction is that this directional chemistry could still be mapped on the sky. If the universe was anisotropic during nucleosynthesis, the primordial abundances of helium and deuterium in gas clouds should not be perfectly uniform across the entire cosmos. They should exhibit a faint, large-scale pattern, perhaps a gentle dipole or a quadrupole, like a cosmic weather map where one hemisphere is ever so slightly helium-rich and the opposite is helium-poor. Modern telescopes are just now gaining the ability to test this. Large spectroscopic surveys that measure helium in hundreds of pristine dwarf galaxies across different sightlines could, in principle, detect such a pattern. The challenge is subtle because the signal would be tiny and easily masked by local astrophysical noise, yet the hunt is on. A detection of a genuine dipole in primordial helium, a directional fingerprint that aligns with a preferred axis, would be a seismic discovery. It would mean that the universe was born with a grain, an orientation that broke the perfect symmetry we have always taken for granted. The physics that could drive such an anisotropic opening is not pure fantasy. Primordial magnetic fields, the same ones we met earlier, could naturally pick out a preferred direction. A uniform magnetic field threading the early plasma exerts a pressure that is different along the field lines than across them, making the expansion anisotropic. Similarly, a rolling scalar field driving early dark energy might not have been perfectly smooth. If it was coupled to the curvature of space in certain theories, it could have spawned an anisotropic inflationary shear, a gentle but persistent tilt that lasted just long enough to leave its mark on the nucleosynthesis era before being diluted away by the later, smoother expansion. The crucial requirement is that the anisotropy must vanish relatively quickly after the first 3 minutes. The cosmic microwave background, released nearly 400,000 years later, shows spectacular isotropy with temperature differences across the sky of just 1 part in 100,000. Any anisotropy that survived until that epoch would have left a far stronger imprint on the microwave radiation than we observe. So the anisotropic window must be brief, a fleeting directional fever that broke just after the light elements were forged. This tight timing actually sharpens the theory into a testable scalpel. It tells us that only models where the anisotropy naturally erases itself through the dynamics of the field or through the universe's own viscous smoothing can survive. Researchers have built numerical simulations that track an anisotropic metric through the nucleosynthesis network, calculating exactly how much helium, deuterium, and lithium will be produced in each direction. The results show that even a modest initial shear, a difference in the Hubble rate of just a few percent, can thread the needle. Such a shear can slightly lower the global average of lithium-7 while keeping the sky-averaged helium and deuterium inside their observed bounds, but it leaves behind that crucial spatial fingerprint. The lithium plateau in halo stars might then be not a flat line but a gentle slope, a variation with position on the sky that future all-sky stellar surveys could uncover. This idea forces us to re-examine a foundational comfort. The cosmological principle has been a faithful guide, but it is not a proven fact of the earliest instance. It is an assumption, one that we test every time we look deeper into the sky. The first light elements may be the oldest and most rigid record we have of a universe that was not born in placid uniformity, but in a directional storm, a stretching, straining geometry that quietly tilted the chemical birthright of every star and planet that followed. So when you look up at a dark patch of sky and see the faint glow of a distant metal-poor star, consider that its lithium might whisper not just about the heat of the Big Bang, but about the very direction in which the bang blew hardest, a hidden arrow of creation still waiting to be read. Deuterium is the ultimate cosmic chronometer, a candle that only burns, never brightens. After the first 3 minutes slammed shut, the universe never cooked another atom of this fragile isotope. Every single deuterium nucleus that exists today was forged in that brief, blistering window, and from that moment onward, its only possible fate was destruction. This single, irreversible truth transforms deuterium into a uniquely honest witness. Where helium can be puffed out by stars and lithium can be chipped away by cosmic rays, deuterium simply dwindles. Any star that forms, any gas cloud that heats up, any whisper of nuclear burning will chew through its deuterium supply and never give it back. This makes the abundance of deuterium we measure a running clock, a chemical meter reading how much pristine primordial gas has survived the chaos of galactic evolution. The process that erases deuterium is called astration, a quiet but relentless devouring. Every time a galaxy pulls in a fresh cloud of hydrogen, shreds it into a star-forming disk, and lights new suns, those suns immediately destroy the deuterium locked inside them. Even a low-mass star barely hotter than a brown dwarf will burn its deuterium in a brief, early flash before settling onto the main hydrogen ladder. The gas that eventually returns to interstellar space from stellar winds and supernova is deuterium-free. Over billions of years, the galaxy cycles gas through generation after generation of stars. each pass through a stellar furnace, reducing the total deuterium budget by a fraction. A galaxy like the Milky Way, which has been vigorously forming stars for most of cosmic history, has therefore scrubbed a significant amount of its primordial deuterium from existence. The isotope we measure in nearby clouds is not the pure Big Bang value but a diminished survivor, a remnant that has survived however many cycles of birth and death that particular patch of gas has endured. This is where the theory of gas infill becomes crucial. Galaxies are not closed boxes. They are constantly fed by rivers of fresh, pristine hydrogen streaming in from the intergalactic medium. These cool streams of gas have never been inside a star. They carry the full, untouched deuterium abundance from the Big Bang. When such a stream pours into a galaxy and mingles with the older, astration-scrubbed gas, it raises the observed deuterium back up toward the primordial level. So the deuterium abundance you measure in a particular galaxy is not just a depletion count. It is a balance between the rate at which stars are destroying deuterium and the rate at which fresh, deuterium-rich fuel is raining in from the cosmic web. In a galaxy like our neighbor Andromeda, the measured deuterium is a delicate equilibrium number, a chemical tug-of-war between infill and star formation. By comparing deuterium abundances across galaxies of different masses and star-forming histories, astronomers can literally map the flow of pristine gas into the galactic ecosystem over billions of years. Then there is the sly trick of dust. Deuterium atoms like to bind into hydrogen-deuterium molecules, and these molecules can get trapped on the surfaces of tiny dust grains floating in the cold interstellar medium. Once locked onto a grain, the deuterium becomes invisible to our spectrographs, which look for atomic absorption lines against bright background quasars. If a significant fraction of the deuterium in a gas cloud is locked up in dust rather than floating freely as atoms, we will systematically underestimate the true abundance. This is a subtle systematic error, one that varies from cloud to cloud depending on how dusty and how dense the environment is. The most metal-poor, pristine clouds, those with almost no heavy elements and thus almost no dust, are the gold standard because their deuterium remains safely in the atomic phase. But even a tiny amount of dust in an otherwise clean cloud can hide a measurable sliver of deuterium, skewing the apparent primordial value downward and creating a false tension where no true cosmic discrepancy exists. These three forces, astration, infill, and dust depletion, all conspire to veil the pure primordial deuterium number, and yet the push to uncover that number has become one of the most fruitful drivers in all of galactic astronomy. The quest to find genuinely unprocessed deuterium, gas that has never so much as sniffed a stellar interior, pushes telescopes to the edge of the observable universe. The best places to hunt are the most distant damped Lyman alpha systems, enormous clouds of hydrogen gas seen in silhouette against brilliant quasars when the cosmos was only 1 billion or 2 years old. These distant clouds formed so early that they had not yet been enriched with dust from supernova, and there had been barely any time for stars to cycle and destroy their deuterium. They are the closest things we have to a direct sample of the primordial broth. Measuring deuterium in such a cloud means capturing the faint absorption line at the very blue edge of the optical spectrum with a spectrograph on a 10-meter telescope, counting the tiny dip in a quasar's light that marks the shadow of an isotope forged 13 billion years ago. Every such measurement is a hard one, painfully precise datum that tightens the baryon density and constrains the cosmic neutrino background. What makes this whole pursuit so elegant is the way it connects the deepest past to the bustling present. The same deuterium atom that survived the first 3 minutes may have drifted for eons in the intergalactic void, then gently fallen into a forming galaxy, swirled for a while in a cool cloud, and finally found its way into the beam of a telescope just as a distant quasar flared behind it. The atom itself has done nothing but sit, its fragile bond intact, while entire galaxies roared into life and died around it. its measured abundance today is not just a relic of the Big Bang. It is a record of every gallon of pristine gas that ever fed a galaxy and every star that ever burned. The deuterium chronometer does more than test the Standard Model. It forces us to understand how galaxies are built, how they breathe, and how the pristine building blocks of creation are slowly, inexorably consumed. And as our journey through the 30 theories comes to rest on this single, fragile isotope, we are left with the realization that the first light elements are not merely ancient fossils. They are active threads woven through the entire tapestry of cosmic history, threads that we are still learning to read, one photon, one nucleus, one ancient atom at a time. 30 paths through the primordial fire have carried us to the same luminous realization. The Standard Model of Big Bang nucleosynthesis is not a fragile house of cards trembling before every passing doubt. It is a granite fortress, a framework so precise that it predicts the abundances of hydrogen, helium, and deuterium with a fidelity that still stuns the scientists who test it. And yet, as we have seen, that fortress has windows left ajar. The stubborn shortfall of lithium in ancient stars, the subtle whispers of possible helium-3 anomalies, the lingering tensions in the baryon density, and the neutrino counts, all of these are not cracks in the foundation. They are invitations. Each one is a door into a deeper chamber of physics, a place where the most ghostly particles and the most colossal forces converge on a single, ancient cooking pot. This is what the 30 theories collectively reveal. The hunt for the first light elements is not a closed chapter in a textbook. It is a vibrant, unsettled frontier. Every exotic idea we have walked through, from mirror neutrons slipping between hidden sectors to cosmic strings cracking the young spacetime, from decaying gravitinos gently pruning lithium to primordial magnetic fields steering the very dance of protons, is a testament to how much we still have to learn. These theories do not just compete, they cross-pollinate. A constraint from the cosmic neutrino background sharpens our search for sterile neutrinos. A measurement of intergalactic magnetic fields tests whether turbulence rewrote the nuclear reaction rates. A laboratory experiment to catch an axion becomes, at the same time, a calibration tool for the cooling of the infant universe. The humble atoms of hydrogen and helium that float in the spaces between galaxies, that stream from the sun and fill the air you exhale, are not silent relics. They are the oldest storytellers in existence. Every time a telescope captures the faint shadow of deuterium in a distant quasar cloud, it is reading a sentence written more than 13 billion years ago. Every time a halo star reveals a stubbornly low lithium line, it is hinting at a hidden actor in the play, perhaps a dark matter particle that lived and died before the first star ever shone. The universe has stitched its deepest secrets into the simplest elements, hiding clues about dark matter, the ghostly sea of neutrinos, and the very fabric of spacetime inside the nuclei that make water wet and stone solid. So as you step back from this journey through the first 3 minutes, consider what it means to live in a cosmos that is still speaking. The story is not finished. New telescopes will find more pristine gas clouds. Next-generation spectrographs will measure isotopic ratios with astonishing precision. Deep underground detectors will catch the faint recoil of a primordial neutrino. And every new data point will either tighten the lid on these exotic theories or crack it open to reveal a new layer of reality. That is the thrill of the frontier. If this voyage through the cosmic kitchen has sparked your imagination, then joining us for the next deep dive is a simple click away. Subscribe and we will keep unraveling the greatest mysteries of the cosmos together, one atom, one photon, one ancient whisper at a time.